Very good morning to all of you. Apa khabar semua, dengar saya ke? Right, good. Alright, good morning. Okay, kita still participation still low tak apa. Ada yang lain Okay, hold on sekejap Alright, Assalamualaikum class. For today, kita go for new topic which is fatigue analysis. Alright, fatigue analysis. Okay, previously we have learned about static analysis. I've already make you aware of free body diagram, force analysis, and I did explain to you about static failures, DET theories, how to calculate safety factor based on mechanical failure based on static. But today in this topic, the next topic on fatigue loading or fatigue analysis. Okay, for example, like the shaft assignment that I gave to you previously, always, and normally shaft, when we do analysis on shaft, when you plot your shear diagram, moment diagram, and you get which one yang critical, either B or C, based on your moment diagram, you combine on both plane, XY plane or XZ plane. What you have done in your assignment that is already explained, the one is static analysis, okay? Because actually shaft is not static, sebenarnya shaft to fatigue analysis. Fatigue analysis because the shaft is rotating. Normally for shaft, we go for fatigue because the shaft, of course, make no sense kalau shaft tu we do static. But you can do static analysis for initially to estimate the size of the shaft, estimation. Initial estimate the size of the shaft, because maybe you can put high safety factor based on static analysis. Remember your DET safety factor is SY, the shaft material over your sigma equivalent, your equivalent stress. Tapi that is a basic equation for static analysis based on DET. Tetapi then you get this maybe by the size of the shaft, you got your static factor, you got 4 point something. It's okay. I mean your shaft too is safe based on static. Tapi normally the shaft is rotated. Shaft is rotated because shaft ni always is driven by motor. Class, you can hear me Class, boleh dengar Shaft is rotating high RPM, high revolution per minute, driven by motor, and the shaft drive another shaft by man of spur gears or pulley and belt. So it means both shaft is rotated. The shaft you have actually is rotated on in high RPM. So actually, when the shaft is rotated, actually the loading that apply to the shaft. Remember before this, you apply loading based on bending, maybe bending combined with torsional. Actually, the bending apply on the shaft. When the shaft is rotated, your element at the top will go at the bottom. Element at the top. Remember when you do motor circle, element at the top, you go for tension or maybe compression. Element is on the shaft. If shaft is rotated, your element also rotated. So your element will face compression, tension, compression, tension, compression, tension, depends on how many RPM of the shaft. So it means your element will facing fluctuating. The loading is fluctuating. It will face tension, then you go for bending load. Tension load, bending load. That's why if you have pure bending on the shaft, tension and bending, tension and bending, tension and bending. It means kalau if you plot your shaft, your bending load, your bending, sigma bending on the shaft, it is fluctuating like this, like a sine wave, where this one you go for tension, because it's positive, and this one you go for compression because it is negative. Where compression tension the same value lah, because if it is completely reversed, because your shaft tu, because katakan you have supported load by bearing and you have bending here, okay? Bending. This is your shaft, This is your shaft. If your shaft is rotated, okay, your element at the top, in this case, for example, you have supporting load at bearing and you have bending load here. So you mean your shaft will bend like this, right? It try to bend like this. Okay, at this moment, when the element is at the top, we're facing compression. When it goes, because the shaft, when it goes to the bottom, your element will facing tension. It goes to the top because shaft is rotated, so element will go top, bottom, top, bottom, top, bottom along the circumference. It's rotated along the circumference. So in facing the bend tension stress, bend compression stress. When it goes to the bottom, it go for tension. When it go to the top, it go for compression. So it means when you plot your sigma bending through times, this is fluctuating loading. So this fluctuating loading, because the bending stress is positive and negative. So it goes like sine wave. So it variable, it varies through time. It varies through time. So if this is the case, remember when you do safety factor based on static entities, and you use DET theory, you know that your safety factor is SY, your yield strength, over sigma E. That is static. But actually the shaft is rotating. So the shaft, if shaft is rotating and you have a bending load, for example, pure bending, so your element will facing tension and compression through time. So we will no longer use static energy because our strength of the shaft is no longer SY. Because this shaft sustain load, because bending load, we calculate stress. The load is fluctuating from positive to negative. The example of fatigue loading. So this will cause the shaft, weaken the shaft material. We can no longer use SY. Remember why fatigue loading is critical compared. We must study fatigue, depend on the, if you're, for example, like rotating shaft. Why fatigue loading? One way to example fatigue loading is, for example, like, okay, for example, like remember when you are a kid, you have a small piece of wire, katakan metal, I'm talking metal, we are talking about ductile material, metal wire. Remember when you were a kid? I remember when during my kid, when we want to break a wire, sometimes we have a small kid project, a wire too, we remove the plastic case and we want to break the wire. We will bend like this, bend like that, bend like this, bend like. If we try to bend like let's say the wire too little bit thick, not so thin, easy we can break it, but little bit thicker. Remember that you cannot, if you just bend one direction, that is static loading, because your loading is just, you just bend one direction. You are not moving like this. Compression, this one is tension, compression, one side. If your element at the bottom, compression, tension, compression. If you just bend like that, you you can never break the wire. But if you bend like this, you bend like that, this one go, okay, this one go for tension, and you bend another again for like this, then this one go for compression, you bend like this, you bend like that, like this, like this. Remember when you were a kid, I don't know if you through your experience, through my experience, then only the wire, if you, the metal wire too, you can easily make it weaken, you bend. I mean your bending is fluctuating, tension, compression, tension, compression, tension, compression, tension, compression. It will weaken the material of the wire. So later, through times, when you do it, then it will break. Your wire will break. The wire too is ductile material. So that's kind of example why fatigue loading. Kalau you just static loading, you just bend one direction, you can never break the wire unless you do it like this, like this, like this, like this, like this, like this. That's why the strength of the wire will weaken, Okay, will weaken. Okay, so will weaken. As I told you, that's why we can no longer use static punya safety factor. We can no longer use SY. So if the weaken, the material, kalau if static analysis, remember SY over your sigma. But in safety factor, we can no longer use SY. It will weaken. So it will be your endurance limit, SN. Over your, this is a basic question, safety factor. This one go for fatigue. This is not the exact, just rough equation to explain to you. This one go for fatigue. SN. SN mean we are no longer yield strength. Remember, static analysis, we use yield strength from the material properties of the material. Tapi kalau fatigue, because since the loading is fluctuating, So it will weaken. We can no longer use yield strength. We will use endurance limit of the material. Endurance limit is lower than your yield strength. It means because we have to be careful because the strength of our material will be lower, no longer SY. Remember for ductile, when you plot you punya apa? When you plot your, remember ductile material, if you go for static analysis, when we go for strain, delta length over length, right? Remember you punya ni, strain, we plot, if static analysis lah, is straight line, then it can become a curve here, then little bit lower, and this one is, ini adalah S ultimate lah, ultimate tensile, this is tensile strength. But for ductile, this one berlaku yielding. This one dah already start yielding. Okay, this is SY because SY the already weakened limit of the ductile material. Once you go for yielding, it means that you punya ductile already weakened. This one for static. Remember when you plot static, we always go for SY if our loading is static. Okay, static. But as I told you, if your loading is not static, loading is static, okay, your loading is static, for example, you bend this direction, so you can no longer use SY, we will use endurance limit. Endurance limit is lower than your static. Actually, that's the question nanti I explain to you later. Class, you can still hear me? Line okay? Class, right? Class? Just to check. Okay. So you can no longer use SY. Endurance limit. Endurance limit nanti you will calculate. What is endurance limit? Endurance limit is what the material, the component that you will see. The endurance limit is not yield strength. It's lower than your yield strength because the loading is fatigue. The loading is fluctuating. So you punya material tu dah weaken. So we can no longer use SY. So we'll use endure. What is the material can endure? So they got endurance limit. Endurance limit to SY and endurance limit. So we need to calculate what is the endurance limit. So nanti I will explain to you. To calculate that SN, okay, remember basic, this is rough. Basic safety factor is SN over your sigma equivalent from your DET lah. Remember ductile, we use DET theory. Endurance limit ni you can calculate. Actually ada dia punya modification factor CL, CG, CS, CT, CR and your SN prime. Okay, dia ada masuk ni. SN prime ni endurance limit based on RR Moore test. It is a standard done already by engineer dulu. Long time ago, engineer already set. Remember kalau you engineer already done for your static loading, they all material they put the data kan. Remember when you look on your at the back of your textbook, all the material properties AISI 1040, you got SY value because already done by engineer. That material they make a universal tensile test, they pull it until what is the value of SY of that material. If you analysis on shaft, that shaft the same material as that material AISI 1040 hot roll for example. So the same material because the engineer does already on standard specimen test tensile test. That one for static. Tetapi okay, for fatigue ini already the standard tests are more done by engineers lah, where they already done fatigue punya pure bending load. Standard specimen they do bending test based on when the shaft is rotated on specimen and they already put the data on that. So this is based on NR standard test. So you means you use the standard test already done, okay, done by engineers of the same material, okay, of the same material that you do analysis. For example, you use AISI 102. So already done, this one standard. So then you have to multiply by these modification factors, where CL is your load factor, CG is your gradient factor or size factor, we call it. This one is CS is not size, CS is surface factor, this is temperature factor, this is reliability factor. This one is pretty straightforward. Nanti I will explain to you later. But multiply SN prime is a standard test by engineer already done. SN they already found out. So we don't have SN2 always for steel material. Is always 0.5 of your tensile stress. For example, that shaft that you choose, what material you look on the table properties, what is the tensile strength, not SY, that you time by 0.5, that is your SM prime. This one is standard specimen test. So you multiply to all the modification factors, CL, CJ, this one. Okay, all these factor, is a factor that we call it modification factor. Modification factor. Modification factor that we adjust the standard specimen test by already done, which is 0.5 SUT. All this modification is one that adjusts to be that one that is suited to your case. The one that you do on shaft analysis. So you ada load factor, you tengok the size factor, what is your shaft, so and what is your surface of your shaft, and what is the temperature when during operation NCR, what is the reliability that you use, like the 99%. So this all the factor modification times this one, that is your endurance limit. Once you dah calculate your endurance limit, then you get your safety factor, where your safety factor is Sn over your sigma equivalent. Tapi this is a rough equation. Nanti I explain to you. Because there is certain thing that we need, other certain thing, like for example, like fatigue stress concentration factor, like shoulder, like groove, they have a concentration. Nanti later I will explain. Also about sigma mean, sigma. Okay, that's a basic explanation about fatigue analysis. A rough introduction. Faham class? Okay, clear? Hello class. Clear or not? All right, please look, open your e-learning. E-learning oh ya. Ini session 8 ni Alright. Okay, can you see my e-learning class?
Yes, Doctor.
Right. Okay, on topic 4. In your learning in topic 4 ni ada nampak tak? Class. Okay, yang ni this is a note ini standard note we use chapter 3 fatigue failure prevention So let's open this slide Okay, hold on. Okay, can you see the slide? Hello class. Okay, design of mechanical failure prevention, fatigue failure. Okay, that's why as I told you, when we bend the rod, the metal rod, ductile material, it will, when we just bend on one direction, it will not fail. When we go for, like I said, repeat on compression, tension, compression, it will fail. Okay. Okay, I just skip through this one. This about fatigue. I think I already explained to you rough explanation. You can read in this one about fatigue analysis. That's why okay, this is a RR Moore test. This is done by engineers already. This is a standard test specimen subject to pure bending. That's how they do the data on this. Because remember, when you do static analysis, you will refer to the SY value. SY value, engineer already done the pure tension, universal tension machine. They push your specimen, then you record all the data until what is the value of the force. If you axial loading, this force, and it will calculate the axial stress, and until yielding value, SY. The limit SY. After SY, it will become elastic. Then the ductile material behave like plastic behavior, so it's no longer safe. Dah jadi lembik, it become elastic already. After if you reach SY value, that one is for static. But for fatigue, the engineer have to do the standard test and not universal tensile machine because they have to use on the specimen where the shaft is rotated. If you look on the figure, it's not. The shaft is rotated, and there is a revolution counter where they measure the how many cycles when the shaft. Okay, when the shaft is connected to the motor. Okay, it's coupled to the motor and the motor run in high RPM. So there's a revolution, it will count how many revolution. One rotation is one revolution. And one rotation, you will count it, okay, they put a weight. And they put a weight. I mean, this shaft, they are supported by bearing. Class, okay, line, okay, boleh clear, boleh dengar. Okay, the shaft is rotated by bearing. Okay, and is supported by weight. Okay, the engineers, this is a standard test done by engineer. Okay, they just mount the weight. Okay, they mount the weight. Okay, for example, they mount the weight. Let's say they mount the most ultimum weight. The weight that's so heavy, and they, okay, if they put the weight that is so heavy that the shaft too will bend and it will just zero cycle, just one pusingan only, just one revolution of motor pump brake. So they will jot the data. They will jot the data. Let me show you. Class, can you see my live video? Boleh nampak class? So they plot the data like this. So they plot the data. Okay, they plot the data like this. Okay, this plot is log 10, log 10 plot. You see, this is number of cycle. Boleh nampak kan? This is your number of cycle. Number of cycle, and this is your strength. Stress lah, strength. So the engineer, when they do this specimen, this is 10 to the power of 0. 10 to the power of 0 because it is a log 10 plot graph. Log 10. It's not a typical graph scale, it's a log 10. Other you can buy from stationery graph log 10. Ada dia jual log 10 graph. This 10 to the power of 0. 10 to the power of 0 is 1 cycle lah. So okay, they mount the weight. If you look on this slide note, they mount the weight and this is a counter of revolution. Just one revolution, it will break. So this is your SUT lah. Kalau logically, this one would be ultimate tensile. Remember this material, right? Ultimate tensile strength will break lah. Will break. Then up until, okay, this is 10 to the power of 1, 10 to the power of 2, counter, in terms of cycle, 10 to the power of 3. It means, okay, they reduce it to the most, if they put the weight is so heavy that it reach the tensile strength of this material of the shaft, that is will be your stress. Just one revolution already break. That's why they put the data here. Okay, ultimate tensile, one revolution that already break. You mean they put the weight that is so heavy that the maximum that can be supported by this border supported by this shaft. Then they put the lower weight. Understand me? Are you with me, class? Are you with me or not? Okay. Then they put the lower weight. Okay, this one SUT lah, of course, logically SUT. Okay, then they put the lower weight, little bit lower than SUT, the weight of the the load that apply on the shaft or that standard. Then they jot down how many cycle will break, like this. You break little bit lower. Then they put little bit lower weight. How many cycle? This one take 10 to the power of 2 is 100, right? 100 cycle, 100 revolution. So they make the data, and 1,000 they make the data. Okay, they plot the graph, and then they found that this one, the graph need a straight line like this. They straight line for 10 to the power of 3 becomes straight like this. Then they measure 10 to the power of 4 cycle. Then they record like this. 10 to the power of 5. Then they record how much the break. It means they lower the weight, because they lower the. This one, the first one, but the most heaviest weight, is close to SUT already. One cycle saja of revolution, then the shaft break. Then lower, then they jot down. And 10 to the power of 4, because this is standard fatigue testing, because the shaft, if you look on this figure, the shaft is rotating, right? The shaft have bending load. It means element as I showed at the shaft have compression tension. It means element of the shaft today facing sigma bending tension. This is pure bending. Tension, compression while the shaft was rotating. That's what it means. So there's the plot, dia punya strength versus cycle. Okay, this is fatigue, standard fatigue testing. Okay, that's why then after 10 to the power of 4, they lower the weight. Okay, 10 this one 1,000 cycle, this one 10,000 cycle, little bit lower. That it takes some revolution. 10,000 cycle lower. It means this lower the weight. 10 to this it will break. At 10 to the power. Then they lower the strength. So it means the strength is lower. Lower the weight, the strength is lower. 10 to the power of 5, they will break. And until, okay, listen up, until 10 to the power of 6, 1 million cycle. Can you see my graph, class? Boleh see my live video, my drawing, class? Well, class?
Yes, doctor.
Yeah. Then they measure the lower the weight until 10 to the power of 6. Okay, 1 million cycle, it will break at little bit. Okay, this is then 10 to the power of 7 cycle. The strength it will break, the remain tak become lower like this. Okay, yang this one is A point, this point A, this point B, point up until point C, BC. BC is different slope, different slope. little bit, I make it, maybe I'm wrong, I will make a little bit sharp to the bottom. Okay, like this. From like this. 10 to the power of 6 is like this. Maybe, yeah, it's something like this, 10 to the power of 6. So where is the data for 10 to the power of 5 to 10 to the power of 6? When after 10 to the power of 6 and above, 10 to the power of 7, it becomes not going down, it becomes constant like this. Yeah, it becomes constant, 10 to the power of 8 and so on and above. Your cycle, and this is your cycle. So it becomes straight line. They found out it becomes a straight line. For all data methodology, the behavior of the graph is like this. When they do the fatigue, standard fatigue punya test, okay, RR mode, this is what we call RR mode test. When they plot for all material, yang ductile like aluminium, like metal, dia punya graph when you plot log 10 become like this. Okay, from 10 to the power 0, 10 to the power 3, so the slope is like this. 10 to the power 3, 10 to the power 6, the slope is like this. This is BC. And this one is apa? Then after that, 1 million cycle, okay, this is what we call SN. Okay, when you go for the up 10 to the power, okay, like this, for 10 to the power of 3, this is your S3 value, strength at S3 mean your strength at 1000 cycle, 10 to the power of 3, this is your strength. Okay, when they put the weight, little bit lower than ultimate tensile stress, and if at 1000 cycle, it will break. That is the strength of S3 is strength of 10 to the power of 3 cycles. Okay, then the data is like this, the SN curve, log, this is a log 10 graph, and kemudian after 10 to the power of 6, it become remain constant, a straight line horizon. That's what they found, right? When you go for 10 to the power 7 cycle, when they increase the, dia become, they remain constant like this. Okay, so this is the value yang ini, 10 to the power of 6, this, after 10 to the power of 6, the data they become like this. The data become, when you include dia punya, apa? The strength is here. See, this one we call endurance strength bar. What is prime? Sorry, the bar is the standard specimen test, not your case, not the one you did. It is a standard specimen RR test, SN bar. Okay, for steel material, see, when they plot this graph, they found out for steel material, pasal kita banyak lot we focus on machine component or steel, don't go for brittle material like cast iron and so on. Aluminium is also ductile material. Okay, for steel material, your S3 here, S3 is always 0.9 of your SUT. S3 ni 1000 cycle punya strength ni is 0.9 of SU, your ultimate tensile strength. Ini you kena take note of this. Okay, and SN ni, are you listening or not? Boleh bawa kayu ni clear or not? What I'm lecturing ni, class. Hello, class. I try to explain the most easiest way. Kalau by slide mungkin you don't understand. You get the picture, what I'm trying. I try my best to explain the most easy way for you to understand about fatigue. Boleh class? Right? Hello, class. So they found out that this SN value after this one, okay, when we go for, okay, this is S3 for 1000 cycle. SN, this one prime is 10 to the power 6 and above punya strength. This is what I call endurance limit based on standard test, RR mode. Okay, for this one, SN that they found out for steel is always 0.5 your FUT. The value of here is always 0.5 of T. So this one half lah, sepatutnya saya draw ni not proper lah. 0.5 of your SUT. Okay, let's say this one is point A and this one angle from 10 to the power 0 cycle, temperature is at B, and this one different slope, more deeper the slope at point C. And kemudian after 10 to the power 6, you punya, ni yang endurance limit. This is not endurance limit for your case, guys. The endurance limit, when I'm talking about RR mode test, standard test already done. But your case, when you do shaft analysis, you have to adjust it with that modification factor that I told you just now. CL, CG, CS, CT, CR times the SN prime. SN prime is 0.5 your SUT. Okay, take note of this. Okay, sometimes, okay, hold on. Sometimes when we do analysis, macam you I cakap the basic, actually the equation for certificate, just this is a rough equation. I cakap you force fatigue, your endurance limit over your sigma equivalent. This is DET, sigma equivalent is always your denominator. This is the strength of your material. But for fatigue, I told you we cannot use SY because we use endurance limit SN. SN over sigma E. Okay, what is your SN just now? Your SN is nanti explain. The modification factor nanti I tell you is pretty easy, straightforward. You can get it from your textbooks. Load factor, gradient factor, temperature factor, surface factor, temperature factor, and reliability factor time your Sm prime. Well, we know that Sm prime yang the one I explained to you, Sm prime is 0.5 SUT. So your Sn prime just now, Sm prime yang standard test, specimen test kamu is 0.5 your SUT. Because your SUT you can get, your material you can get from the table properties, right? At the back of your textbook. Okay, AISI 120, not search for tensile strength, not yield strength. Then you got your SUT, tensile strength time, that is your Sm prime. Then you multiply by this modification. It is easy. CL load factor, kalau bending is 1, gradient factor for shaft diameter, other factor. CS surface factor, tengok the shaft tu dia punya surface finish, other factor you can get. Temperature factor, other factor based on temperature when during operation. Reliability factor is given, kalau 99%, other factor not given, we go for 50% is 1. Okay. Now this one, the standard test 0.5. So you can get your SN. So your SN here, your denominator your sigma E. Remember sigma E? Okay, this is a rough equation. Actually, this is not the exact equation. Your sigma, remember your sigma E is kalau you have biaxial strength, remember sigma x square plus tau xy square, or maybe sigma E kalau you principal sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. Remember you punya static analysis. Then you go for the method. Okay, I want to explain. When you got your static factor, you find that your static factor is 0.67. It means less than 1. It will fail. Nampak tak kelas? Hello class, are you with me? Class? Okay, it will fail. It will fail. It means you do analysis on shaft, you do fatigue analysis. Pasal the shaft is rotating actually. For shaft actually driven by motor rotating, no, actually it's no fatigue. It's sebenarnya more accurate to predict, to make design the shaft, either the shaft fail or not. You want to design, you go for fatigue analysis. Okay, from this basic equation, the shaft is failed 0. less than 1. So it will break. It will break. But you can estimate by this log, but by this graph, you can predict when it will fail. Because remember, this is the plot of your strength and your cycle. You can predict what is the strength. Okay, of course kita cakap the shaft will fail. Kalau the shaft will fail, it means the stress that you calculate at this denominator is greater than your Sn. It's greater than your Sn. So it means this is your Sn. Even this is a standard specimen test. It can actually your graph, your case, when you do analysis, the plot of your graph is the same like this. Understand the class? Even this is standard RR test. Your case, the shaft, when you do analysis, for example, on shaft, the plot of your graph log time is the same behavior as this, but it little bit scaling, little bit other more. That's why the modification factor, I told you, CL, CGCS, all these modification factor. The plot of the graph is the same. So this is your endurance limit, your Sn. So it means if your denominator is greater than Sn, it means you punya strength is little bit here, somewhere here, is bigger, right? Understand the class? The strength you calculate sigma E ni is somewhere above your Sn, because this is your Sn value. So you can you do the graph ni, log 10 graph, you can do this. You can bring your line. Okay, this is your case punya stress. You punya fatigue SF, fatigue stress. Okay, SF. You can bring your graph here, and you can bring here, and you can estimate at what cycle it will fail. Clear tak, class? Clear tak apa saya cakap ni? Class, are you with me or not? Okay, then you can see what cycle it will fail. Okay. All right. If you look, right, I hope you understand what I'm talking about. Okay, if you look on the slide, no, okay, that's why I'm talking now about SM. Okay, this graph ni, explain to you about what finite life. Okay, if you look on my sketch ni, okay, if I draw it again, I draw it again the graph ni. Okay, you punya this, you punya ni SN curve, SN curve. Okay, this is your SUT of your material, and we have 10 to the power of 3 is here. This one 10 to the power of 3. This one 10 to the power of 0 is one cycle. Okay, you have line. Okay, your case punya plot of you punya case analysis, you punya case, you use your SUT. You plot log 10 punya graph. Okay, this will be your point A, this will be your point B. Okay, 10 to the power of 3, then until 10 to the power of 6, this is a point C, different slope, the little bit deeper slope. Deeper slope. Straight line, it's a straight line, guys. Straight line. Betul kali. Okay, B is here. It's 10 power 1000 cycle. This is your AB. AB. Then 10 to the power of 6. 10 to the power of 6 is here. So this will be your C point. So this one different slope. Kita punya point of consideration, kalau your center factor field is along like this zone, this zone. Normally as this between 10 to the power 6 to between, okay, this one 10 to the power 6 and above, and above 10 to the power 6. Okay. Yang kita cakap ni, cycle ni, because this is strength, this is cycle. Yang the cycle that we consider, if you look on this one we consider is low cycle. Low cycle between one cycle to 10 to the power of ni, this is low cycle. Low cycle, 1000 cycle to above, consider high cycle. 1000 cycle and above go to high cycle. Remember, low cycle ni like close to static analysis lah. 1000 cycle and above is like close to static analysis. One cycle ni like static analysis. Your border is SUT. Tapi sebenarnya for static data is SY lah. But the plot of the graph, because the standard RR mover, it wait until it break. Break to mean tensile strength. Actually for yielding, because it's my ductile RR mover ni, because when they do the RR mover test, for this case, they wait until the shaft break. Break means it get broken. Broken, it means your ultimate strength, not yielding strength. You already it become break. The worst, the maximum stress until it break. That's why they plot the data SUT. Tetapi SY itu sebenarnya it's a little bit lower lah. SY tu dah start yielding lah. I hope you understand what I mean. So the plot dia use, okay, static analysis, the limit is SUT lah. 1000 cycle, the limit is S3. S3 itu 1000 cycle. Okay. Yang ni cakap SN, this is your SN value, guys. Your case, I mean, your case sebenarnya you punya plot, your graph SN. Okay. Tetapi kalau kita compare dengan RR mu, SN prime lah, because we have the modification factor. CL, CG, CS, TCR, this is standard test done by engineers untuk specimen test standard. So we have to use modification to factor to adjust to this. That's why we have our graph like this. The graph plot is still the same, but the value too little bit this times the modification factor. So this after 10.6 it becomes straight line. Okay, this one high cycle. Okay, if we go for in term of life, kalau if you look life yang between one cycle to 10 to the power of 6, ini we consider it as a finite life lah. Finite life. Okay, 10 to the power 1 millisecond and lower, consider finite life. Kalau sometimes design, that's why when you find your safety factor to less than 1, it means you punya life tu not finite. Kalau you design your safety factor yang tadi N itu Sn over sigma E is greater than 1, it means your life, your specimen tu is infinite life. So dia selamat for infinite. 10 to the power 6 and above cycle, this one is what we call infinite life. From here to and above is infinite life. Okay, sorry, kalau you buat analysis on fatigue, generally we go for infinite life lah. Of course we go for infinite life kan. Tetapi kadang when sometimes you found out your safety factor, like I explained to you tadi, just your N over endurance limit over your sigma E, you get less than 1. Sometimes you can predict at what point, when the stress that you apply on your specimen is greater than your Sn. From here you can use, okay, what cycle that it will break based on this graph. Tetapi we don't have time lah guys. We want to plot log 10 punya graph kan. We want to plot log 10 here, we have time. Okay, tapi we have a standard equation like this. Dia punya AB like this. Okay, they already done the equation lah. Sometimes if your safety factor to less than 1, tengok sini. Class, are you listening or not? Hello class. Class. Line okay. Okay, if you look on your slide, your notes, okay, if you look on the figure ni, for line BC ni, nampak tak class? Hello class. Okay, this one. Okay, for line BC ni, kita boleh predict. Okay, SF ni is your case, your analysis, your fatigue stress lah that you calculate, and you remember that your SN over your sigma E tu, sigma E denominator, you calculate. Okay, the basic equation, your SF is Cn over A. Okay, if you look my, betul tak? Pasal this is based on this graph, guys. Pasal kita tengok, kita punya SF, this is our SF lah, SF we call, because since our center factor is less than 1, it means the stress that we calculate on our element when our analysis, remember you buat plot shear diagram, moment diagram, both plane, and you find out if B is critical, you combine the moment MSY square plus the moment MSZ square at point B, since B is critical, the greatest moment, summation, square root. Okay, then you calculate the bending stress sigma 32 moment at that point B over pi dq. Okay, that's your bending stress. That's your B or the denominator. And then also you find the sigma E is your sigma x square plus 3 tau x square. If you have torsional stress, combine the torsional stress. Then you got your sigma E, right? Your sigma E tu, that is your SF lah. SF is greater than your SN. SN is what? Your nominator. SN, CL, CG, CS, CT, CR. CL apa? CL, CG, CS, CL, CG, CS, CT, CR, and SM prime. SM prime is 0.5 SUT. That is your nominator. Your SN tu, your bottom denominator tu is greater than your punya endurance limit SN. So you will fail. So if you say it's greater, your stress is greater than your SN here. Can you see? It's greater than. So what cycle it could be? I said you can do, this is a question based on this graph. If you look on your notes, that is the question. That's why it stated that you punya fatigue stress that you calculate equal to C times N to the power of A. Nampak tak your notes tu ada tak kelas? Hello kelas? Kelas? Okay, tetapi yang kita nak cakap, kita nak predict what cycle kan? So yang you can see the bottom equation. Bottom equation. N tu cycle lah. This is cycle. At what cycle, you punya analysis lah, at point that you analyze tu, on shaft tu, this is cycle. How many cycle? How many revolution? You can predict the failure. For how many revolution it will fail. Understand tak? How many revolution? We can predict. Sometimes we can predict. From that, kita boleh design macam mana. Okay? Kita boleh design for how many cycle that we need. Mungkin sometimes there is certain component design. They don't go for infinite. They go finite. Pasal dia ni always be replaceable. Because they try to play, ada sebab, ada sometimes maybe, tapi jarang lah. Ada case yang implement dia go for finite life. Ada sometimes happen. Pasal dia ada reason. Tapi normally kita, sorry guys, I make correction lah. Tapi kalau for design, normally we go for infinite life lah. Infinite life. Tapi kalau you punya, that's why you calculate your static factor to less than 1. Sometimes the question, sometimes in exam question, okay, you find out your static factor is less than 1. They ask you for how many cycle that it would break. For how long? How many revolution that cycle. So you can use the equation. So if you look at the bottom equation tu, sigma N tu is your, you punya you punya sigma revolution ni, is actually you punya stress tu lah, completely reverse over your C 1 over A to the power of 1 over A. So you punya sigma revolution ni actually your SF lah, your SF kan, you punya stress that you calculate over 1 to the power of A. So from here 1 to the power of A. So this one ada what is C kan? This is your stress that you calculate, your nominator, okay? Your fatigue stress to the power over C. What is C? C already given that. C is S3 over Sn. Nampak tak kelas? Okay? S3 ni to the power of 2 over Sn. So what is S3 just now? S3 tu yang I cakap 10 to the power of 3, 1000 cycle. What is the strength? What is the strength here? S3 value yang 10 to the power of 3 when ni dia punya limit. Kalau 10 to the power of 3, what is the strength of you punya ni lah, you punya analysis. S3 dia value is apa? Remember dalam standard test dekat S3 is apa? S3 is 0.9 SUT for steel. Ini valid only on steel. Okay? Only for steel. Kalau different material lain. S3 is 0.9 your SUT. And also SN 0.5 SUT only on steel. Pasal kita banyak fokus, we more focus on steel material. Okay, then already get your S3 itu, we know that S3 is 0.9 of your ultimate tensile. Ultimate tensile can get from table properties of your material. Okay, Sn tu, what is Sn? Plus, Sn tu apa? I want to test either you are with me or not. What is your Sn? Yeah, your endurance limit lah. Remember, SN endurance limit. Yeah, actually, yeah, betul, you're right. Your case kan, pasal you modification method, this is RR Moore test. Kan, your case ni, your SN ni sebenarnya guys, pasal you punya case, your SN ni, yelah, is 0.5 of your case SUT lah. Okay. Your SN, you ada modification factor lah. SN ni adalah infinite lah, you are infinite life, your SN. SN ni, you punya case is, you already calculate pasal kita punya case, kita have to adjust modification factor CL, CG, CS, CT, CR, and your SN prime. We know that SN prime is 0.5 of your tensile strength SUT. Ni you boleh dapat. Then modification is straightforward. You boleh get from table. Nanti I explain to you how we get this, all this modification factor. So that is your SN. SN you put here. S3 is 0.9 SUT, right? So you got your C. So C will be put here. So 1 over A. What about this A? Pula? A is 1 over 3 log SN over S3. S3 tadi is now 0.9 SUT. SN tadi yang this one. Okay, 1 to 3 log. Clear tak guys? So you put here, you get your, ni, you got your cycle. Okay. Yeah, sigma revolution tu is your, actually sigma revolution is complete reverse lah. Is your SF lah. Pasal the equation from here kan. SF2 means we want to predict SF, what is the cycle. Actually from this graph log 10, SF, okay, because you punya stress that you calculate above your endurance limit. So it will fail. It will fail. So but you want to predict based on this log 10. You want to, actually the equation is for line BC, log 10. That's why I don't want to explain to you this one more complex lah. Log. Actually this is how they derive it. Can you see the notes? They derive why they make it simpler this one. Okay, actually SF, okay. You punya CS itu tu, then you punya, itu is stress, fatigue stress that you calculate. You calculate. Remember when you do your ice cashier diagram, you get the critical sigma bending. You combine dengan principal stress, you got your sigma equivalent, right? Kan? DET sigma equivalent is kalau you have biaxial stress sigma x square plus 3 tau x square square root of that sigma. That sigma equivalent lah. Sigma equivalent. The stress on your B, let's say B at your shaft at point B is the most critical. You calculate the sigma equivalent because we are based on DET. Okay? Okay, that is your SF. Yeah. In this one, they put sigma revolution. Yeah, that's why I put this one as well. Nampak tak? Actually, dia ni lah kan. Ni, actually from the equation, SF is Cn over Cn to the power of A. Then you derive it back. Since A is this, and C is this one. Then you put into here. Then you got this one. This sigma revolution is your SF. Okay, guys? So you can predict lah. You boleh predict how long it will, how many cycle. Because N is number of cycle. Okay. All right. Okay. If you look on the slide, I already mentioned to you. Okay. SN bar for steel is 0.5 estimate strength. Standard test already done. When they found that your standard SN prime is 0.5 SUT. What is SN prime? Yang standard test. Remember standard test that I mentioned to you, yang they done the RR Moore test. Okay, this is standard test, specimen test, 0.5 SUT. Okay, 0.5 SUT. That's why you punya case different, you punya shaft different. Pasal the engineer done tu, dia punya specimen tu different diameter shaft kan. Dia one different, tapi the same material lah kan. Tapi you punya case different, you punya shaft at specimen at point that you analyze yang critical tu different. That's why we cannot cakap our endurance limit the same as standard test. We cannot say. That's why we cannot kita tak boleh cakap that our SN of our case equal to SN prime. Understand tak guys? We cannot say like that. SN prime is standard test. Standard test already done by engineer, standard test. Where this is RR Moore test. Yang tadi yang figure tadi, they put a counter kan, RR Moore test. You cannot be like that kan? Pasal our case tu, our case different. Pasal the size of our shaft is different, the temperature is different, our reliability is different, our size of the shaft is different, surface of our shaft is different. That's why we have to adjust it. So our SN ni, we cannot say it like this. We cannot say it, cannot be like this. So we have to adjust CL, CG, CS, CT, CR, SN prime. SN prime tu yang tadi R-AMO tu SN prime yang they found that your SN prime from the standard test is 0.5 SUT. So we cannot say that our is terus directly 0.5 SUT. Wrong lah. Tak boleh lah macam ni guys. Kita kena modification factor. Our case. The first thing in fatigue analysis, you calculate this first. Because itu nanti, you want to know the limit strength. And you did what you call endurance limit of your case. Clear kata guys? Nanti I explain to you this one. Clear tak? Class? Okay? Boleh bawa lagi tak susah pun, senang ni student cakap oh difficult, tak ada, actually not difficult, straightforward as long you get the picture what I'm trying to explain. You ada record kan? Somebody recording, saya lupa cakap tadi from the beginning. Okay, thanks Ijan, thanks. Okay, you ada record nanti you boleh refer to the video Ijan, you share, nanti you boleh, kalau tak apa you rewind balik apa my explanation. Okay, ini yang modification factor. Okay, if you look on this note, modification factor, this is our endurance limit. Okay, this one we have to adjust to our case. This is our case, endurance limit that we want to calculate. First thing, fatigue analysis, you kena buat ni dulu. Fatigue analysis, you kena cari dulu endurance limit. Pasal endurance limit ni, you can get it earlier. You can get it earlier. Okay? Because SN prime, okay, but always in question in your assignment or your exam, the given, the shaft material too is given. AISI 1040. So you can straight away get, okay, SN prime, you know 0.5 SUT. You get from the table properties, the AISI 1040 hot roll, what is the, not SY, SUT, tensile strength. Before this, we use yield strength, no, tensile strength, ada table properties there. Beside that, tensile strength, okay, you know 0.5 of that tensile strength. Then your SN prime, then you can multiply by this modification, CL, CG, CS, CT, CR. Okay, I want to explain what is this modification factor. Boleh Boleh Okay, what is CL? Load factor. Kelas, kemudian nampak no? Okay. All of you buka textbook sekarang. Now. Kelas, dengar tak? Open your textbook. Jom in the textbook. Okay, belajar. Okay, can you see my textbook? Okay, what page is fatigue analysis? What topic is it? What chapter is that? Fatigue. Fatigue analysis is chapter 8. Nampak sini, chapter 8. Kelas? Chapter 8. Chapter 8. Okay, kita skip through. Kalau boleh you baca lah. Baca ni lah, tak pasal yang mana yang important baca. I try to explain to you the most easiest way lah. So everything is in textbook. Okay, I want you to focus on this. On page, tu saya cakap all material, dia punya plot like this. Like rod, magnesium also kind like plot dia macam tadi cakap like SN curve. Tapi kita still is like this. Already explained. Okay, just now, okay. On page, alright. Okay, yang I cakap about endurance limit tadi, you on page ni, page apa ni, this page 299. Ada tak SN prime times CL, CG, CS, CT, CR? Kelas? Ini kita 2 jam kan? Kita kelas 2 jam kan tu dia? 2 hours kan? 3 jam. I thought 2 jam. Okay, saya straight forward boleh tak break? Boleh, it's okay. You want to break, you cakap nak break. Siap lah. Kalau 3 jam kita ada break, sorry. Nanti saya sambung dulu. Before kita break sekejap. Okay, yang ni formula. This is a formula I told you, endurance limit. Our endurance limit times to the yang standard test, SN prime standard test, 0.5 ST times CL, CG, CS, CT, CR. Okay. If you look on this, okay, this page 300. Okay. Ini you kena, how do you bookmark? Kalau nanti dalam test nanti, you always tak payah in digital book? How do you that? You know, kalau physical book you boleh tag stiker kan, you boleh buka. Kalau digital, how you do that? Pakai ni PDF viewer ni. You know tak maksud saya? You terus boleh dapat bookmark. Tahu buat kan kelas? Nanti you tak scroll like this kan, nak cari buang masa kan, during your exam especially kelas. Your exam is online kan. Nanti you just click that it goes this. Macam mana? How do you know how to do that? Saya tak tahu. I'm not IT person. Macam mana? Highlight actually. You bookmark macam I cakap this important. Ha? Ya, Control F lambat. I know. Ada search ni. Tak, I mean this page you want to bookmark. Nanti you click. How do you do that? Ada someone knows about this? Yang lain? Ijan, you tak tahu Saya pun tak tahu. Macam mana? Highlight Macam you click at one point, you book, kan you book kan, you can put when your physical book kan, you can what we call it bookmark lah. You pass sticker then okay, this is about table properties of this. This is table 8.1. Dan terus you buka table 8.1. Kalau digital ni macam tahu? Tak tahu. Pasal saya tak tahu, saya tanya korang ni macam mana. Kalau you pakai PDF viewer, ada kan, you know how to do that kan? Nanti you don't waste time to scroll. Nanti you just click, that is go table 8.1. Okay? Make sure that you know that class ada cara dia, saya pun lupa. Ini saya pakai Microsoft Edge. Actually kalau saya pakai PDF viewer tu is much better lah, ada. You just bookmark. Okay, table 8.1 important guys. Tengok. This how you get your value of all your CL, CG, CS, CT, CR. Okay. Okay, CL is the load factor. Remember CL. CL is the load. CL load factor. Right. Okay, endurance limit. Okay, if you look my live video again, endurance limit. Our endurance ini yang you calculate dulu. Normally if I say you calculate this one. SN is CL, CG, CS, CT, CR, SN prime. Okay, kita know that SN prime, kita straight away dapat 0.5 of your material SUT times 0.5 in megapascal. Okay, CL, load factor. CL, if you look on this table 8.1, okay, table 8.1 CL, kalau is bending, nampak tak? This is load factor. Normally kalau case shaft, remember class, okay, if you look my live video, you punya shaft analysis ni kan, you ada always supporting load, then you ada bending like this, and the shaft everything, maybe you have ada plus dengan torsion. Okay, kalau you might ask me, sir, which one you want to use? Is it bending or axial or torsion? Okay, normally on shaft, remember when you do shaft analysis, shaft can normally, you have shaft. If I draw your shaft, you have a pulley here, and maybe you have a gear here. Remember, you have a gear, this, okay, this is F tangent. Gear top, this one, top this direction, this one, this direction top. And you have T1, and you have T2, and you have bearing here. Bearing, you have loading like this. And maybe at the end, you have another bearing loading like this, and loading like that. Okay? And you have something like this, SY plane. Maybe you punya T1, T2 tu not this direction, can go for that direction. You have two plane. This one you have to consider two plane, SYZ, SY plane. You understand what I'm talking about, guys? Okay, along your BC, this is A, B, C. Along your B and C, which one? Say B critical. So you mean your B ni, okay, remember you buat shear diagram kan? Shear diagram like that. So you have something like this. Not sure your gram, then kemudian you have a V like that, and kemudian at SY plane you have another moment like that. Okay, you found out B2 is a critical, bring critical combine all the both plane, and okay, in this case, or like we do this shaft analysis, which one you want to use? You want to use load factor based on bending or axial or torsion? Do you understand me, guys? That's why you are the confused actually. Which one, sir, do I need to use? Bending or axial load? In this case, bending or what? Why is it critical in this case, like this shaft analysis? Guys, I know B is critical. I mean, what type of loading yang in our case for shaft? Which one yang critical? Is it bending or axial or torsion? In this case, do we have axial tak? Okay, axial is along X, X along X. This is Y, let's say this is Z. Do you have axial? Do you have any stress on axial in this case? Do you have axial loading? No, no, no. Shaft like this. Do you have axial? What? Axial stress. Do you have any axial? Any force along the shaft? Do we have axial loading? Yeah. Top we have, yes, yes. Top we have. Long B. B, remember B, when you look at element at B, you have sigma X, right? Sigma X. Okay, sigma X ni, jangan, this is not axial. This is sigma X based on bending, guys. Do not confuse. The sigma is based on your bending. But we don't have axial loading. Remember that you do NLC, we have also sigma axial yang case yang rod, the one itu we have you punya assignment, remember your rod kan? At point A tu, yang rod AB tu. The one we have axial. Tapi in this case, like shaft, for example, we don't have axial. Okay, in this case, shaft, but we have torsion, right? Torsion, yeah, torque XY. Torque XY here, torque XY there. Okay? Okay, in our case, I'm talking, okay, this CL is load factor. What do you want to use? Bending, axial, or torsion? Guys, I need your opinion. Apa dia? Masa we need to find endurance limit, right? SN is CL, CG, CS, CT, CR, and SM prime. SM prime, we can get 0.5 ST. Now, first one is CL. Which one do you want to use? Class. For this case, like shaft analysis. Hello, class. Are you listening or not? Bending, axial, or torsion? Yeah, we don't have axial. In this case, okay. Okay. Normally for shaft, we go for bending. That's my point. It's one. Okay? Understand that? Hello, class. Yeah, that's my point. You go from it. Unless, remember you have torque, SY kan? If you find out tau XY in megapascal, is it greater than sigma X? Normally for shaft, always yang critical is bending. Because shaft ni, you mount you punya pulley, you mount your gear, you always trying to bend the shaft. And the shaft is rotating. It means your element tu facing compression, tension, compression, tension, compression, tension. The critical is bending. Tapi sometimes, be careful, sometimes maybe your torque tu is much bigger than your bending stress. Be careful. If your torque, maybe you have some like a small high like cruncher. That is the case. You punya shaft is like a cruncher. That kind like you punya system of your machine. They use that you have another pulley or system. I don't know. They use a lot of force tangent and also force tangent is bigger. This go for this direction to twist or something. Maybe that special machine. The torque too is much bigger than the bending. Be careful about it. If that the case, if the torsional stress is bigger than bending stress, be careful. You cannot use bending. You go for torsion. Nampak tak? Value torsion 0.58. Clear class? Class clear or not? Perfect. Okay. Axial rally, unless kalau shaft tu sometime in question exam, sometimes there is macam bevel gear. Bevel gear they have axial ni. Have axial ada. Bevel gear, you know bevel gear tu they have, tapi kita tak learn. We use spare gear in this course. Bevel gear they have three component. We have F tangent, we have F radius, and F axial. The axial tu could produce axial stress. Tetapi the axial stress tu normally is low. Normally we go for bending. Tapi be careful, I'm talking about torsion tu. Sometimes the torsion value tu govern, ini bigger lah. Torsion tu govern. Which one is governing? Sometimes the torsion, tapi rarely happen. Tapi depend on machine. Ada certain machine macam they kind like twist, they kind ada torsion tu is much bigger than the bending. Because for that one, you have to use torsion 0.5. Tapi normally the case for shaft, like power transmission, hello class, are you listening? Bending, 1. Okay, bending, 1. So you punya CL is 1. 400. Mana tadi? Okay, you punya CL ni 1 lah. Okay. Okay, what about CG? CG is gradient factor. CG, can you see the table 8.1? Guys, are you watching the table 8.1? Okay, plus. Okay, CG is size factor. The shaft that you are analyzing, the shaft you are analyzing, be careful, there is certain, okay. The shaft, okay, normally kadang-kadang kelas, you punya analysis nanti, you punya assignment, when you go for fatigue, you punya shaft ni is no longer plain diameter, guys. Guys, are you listening or not? Sometimes it will be like this. Class, and this is your bearing, you have load, your bearing, maybe you have mounting, okay, you punya pulley is here at this point. Class. Hello, class. Are you watching my live video? Okay. Okay. Step shaft, step shaft, you have bigger diameter D and you have smaller diameter D. Because your punya section, okay, point B, this is your point A, this point B where you mount your pulley. Maybe you have another gear kat sini, point C. And this one will be your bearing. And this your D, A. Or your pulley will be here. This is your mounting your pulley at the shoulder of the shaft. Okay, this one, the diameter shaft ni, because normally your previous assignment, your shaft is just a plain diameter, right? Plain diameter. Okay, tapi normally in case it always be step, step. Pasal we mount the pulley, there will be a step at the shoulder, so the gear will be blocked by the step. Dia tak go misalignment. Okay, the pulley. Okay, the diameter of the smaller diameter. Why? Okay, the diameter of the shaft to where is okay? Your B to what is the, because we have smaller diameter, bigger diameter. We go for smaller diameter. Class, just take note. Okay, the diameter is the mentioned diameter of your shaft. Tapi be careful when you have step. Where is the critical point? It will be the smaller diameter. The diameter that you calculate. Okay, tengok guys, CG table ni. If the diameter yang smaller one, pasal B is on the smaller diameter, it's not on the big diameter. Okay, point B tu where you mount your pulley or your gear. The diameter tu is between less than 10 millimeter. Okay, and our case is bending, kan? Okay, just now we mentioned our system power transmission bending lah, because our load factor we use bending, size factor also we use bending lah, is one. Kalau your diameter of shaft is on the question of your assignment, diameter is not 10. Kalau you said 10 mm, you cannot use 10 yang you use the second one. You said less than 10, katakan 8 mm, less than 10, so is one. Okay. Okay, untuk bending ni, kalau axial, you have axial, tapi rarely happen lah. In case kata you have axial, this is the range. Kalau you have torsion yang the govern thing, one. Okay, clear tak clear? Okay, kalau you punya diameter tu, the point yang you analyze, what is the diameter tu, is between 10 mm to 50 mm. Because normally shaft is between 10 to millimeter lah. Or kalau 10 mm, you use 0.9. Not 10 is not 0, not 1. This one is less. Yang the first range ni is for less than 10. But the second range is for 10 mm and above. Clear tak kelas? Kalau 10 mm, you use 0.9, not 1. Oh, hold on, my mistake. Ini, yalah, less than 10. Ini is inci, this is 10 mm. Okay, less than 10, you use 1. Kalau, okay, kalau case bending, okay, normally kita go for bending. If you punya range is from 10 mm to and above to 50 meter, because normally machine no shaft larger than 50 millimeter. 5 centimeter is big, guys, and big shaft. Ini kalau above 50 millimeter ni shaft big high apa tu high power punya machine lah, shaft kapal itu tak ada lah. Kita rally kita machine component shaft between 10 millimeter to 50 millimeter lah. Okay, if that the range of your shaft, the point that you analysis, you go for 0.9 for bending. Okay, kalau axial like this and torsion also 0.9. Okay, clear? Size factor, gradient factor, that is size factor. Clear, class? Alright, okay, be careful. Okay, now surface factor. Okay, surface factor, be careful. Surface factor, you don't use table ni tak give you the value. It's not, this table does not give you the value. See figure 8.1. This one you use graph. Class, CS. Okay, page what? Figure 8.13, class. Then dia dah pointing sini kan. Okay, click at figure 8.3. Okay, page what is it? 498. Figure 8.13. That is your surface factor. Nampak tak ni? Figure 8.13. Class. Hello, class. Page 298. Ini pun you kena bookmark. Tadi yang table 8.1 tu you bookmark juga. This one also you bookmark lah. So easy nanti during your exam. If you want to do assignment, you don't have to scroll everything. You click, then it will go bookmark and go to this one. Alright? You can do that, PDF viewer, right? You can do that. Okay, guys, are you watching this figure 8.13 class? This is surface factor. This is CS. Tadi load factor, tadi gradient factor CG, and now CS surface factor. Okay, surface factor. Okay, this surface factor, if you look on the x-axis here, is your tensile strength, because you know the material of your shaft, for example. You already given the AISI 1040, and you know what is the SUT. You get the SUT from the table properties at the back. Appendix C. What is the tensile strength? Not yield strength, tensile strength. Okay. The first axis ni is on English unit KSI, but you use the bottom one ni, gigapascal. Nampak tak? Kalau is mention that 6, like for example, like you punya you punya SUT tu is SUT tensile strength tu 870. So 0.87 lah, because this one gigapascal. Clear class? At the table, your table properties of your tensile strength 870 megapascal. So you divide by 1000, that is gigapascal, 0.87 between here lah. Class, are you watching or not? Class, katakan your SUT tu, you got example SUT from the table property appendix C of your material is 870 megapascal. But this one, this graph, gigapascal. So you divide by 1000, 0.87 gigapascal. So in between here, nampak draw. You jangan pakai draw macam ni guys. Even you digital book kan. Kalau you digital, I think I suggest you in exam, you print lah. You print this thing. Susah you nak buat digital. Macam mana I nak buat ruler ni. Ini saya pakai tangan. Ini pasal ini 8. Ni 0. Ni yang tengah ni what? Plus. Ni 0 berapa ni? Plus. Ni 0.8. Ya, 0. What is 0.87? Ni 0.9. 0.87 mana? You jangan pakai cara saya guys. In test you pakai, you print this thing. Okay. Laser printer. Print this graph and you do pencil. Pembaris your ruler. Use your ruler. You okay. 8.87 somewhere here. Okay. Do like this. Not 8. Tengah is on 0.85. So you have to be a little bit accurate guys. Pasal you just use you mark that. Apa ni? You estimate that accurate lah. Jangan rough run. Kadang ada some student dia just take jangan value dia lari nanti. Your factor, your Y is your surface vector CS. Try to do it accurate by ruler. Where is 0.7? Okay, clear class? 0.7 somewhere here. Okay, I have to use by hand ini terpaksa lah. So you use your ruler, bring it up. Tapi sir, kita nak intersect which line sir? Which line do you want to intersect ni? Nampak tak? You have a lot of line here. Nampak tak class? Are you watching or not? Class? Hello class? Okay, shaft normally class. Remember, you pernah ada bengkel lab lathe shaft, tahu tak shaft? You want to do shaft, apa machine we do? You want to make a step, kita lathe. Tahu kan kita shaft kan rotating on the lathe machine. Then you your tools kan, you lathe into certain diameter. Betul kan class? Have you done this tak before pandemic? During your lab ke? Ada? Lathing kan? Sekolah teknik yes. Apa ni? Lab betul lah, too bad lah kan. Siapa sekolah teknik sini? Technical school? I remember dulu I'm also from technical school, sekolah teknik. Ada bengkel kan, kita lace the shaft kan. Step shaft kita make kan. Betul tak kelas? Hello kelas. Yang lain senyap aja Yang lain bersuara sikit kelas. Ijian aja bercakap. Yang lain okey. Satu lagi yang siapa? Yang tu. Yang lain mana? Hello kelas. For shaft ni, kita apa? What type of machine kita buat? Kita lathe right kan? Lathe. What is the lathe? Normally shaft kita lathe kan? Kita lathe into certain diameter. Lathe. Kan lathe machine kita lathe. Lathe using the tool, kita lathe, we will lathe. Okay, which one? Which line? We want to use. Nampak? This all you punya machine process of your shaft. Which one? Class? I need your opinion. Which line that we know that our 0.7 will bring it up. We want to intersect which this all these thick line. We have a lot. We have forging, we have hot roll, we have machine or cold round, we have fine ground. It is grinding. I mean the shaft to really polished, the surface to very smooth. They grind the shaft. And the most upper one, like straight one, is mirror polish. The shaft to mirror polish. Mirror, I mean the shaft surface to become mirror like mirror. Do we need our shaft to be mirror polish? No need, right? What's that class? Hello class. Yeah, you are right. Lathe is machine, right? Kan? Lathing. When you lasing the shaft, it's machine process. Machine. So normally, guys, take note. Always machine. Or cold run. Hot roll, no. Hot roll ni class. Hot roll is the basic. Remember, when shaft raw material is a cylinder, right? They produce the cylinder by hot roll. Remember they melt the what they call the billet in the furnace. At the inilah macam like pewajah antara steel Pasir Gudang, pewajah steel Terengganu yang big apa manufacturing steel material lah. They have a furnace. They melt the billet and the furnace. Then the output of that furnace is a molten billet, and the molten will be rolled on the die. The die either want to make angle bar, box section, or shaft, a solid shaft. They roll forward, backward. Then they become a long shaft. That one is hot roll. Tapi belum lagi. Okay, hot roll ni. Okay, then they will sell the shaft to they will send the shaft to the supplier. The supplier sell the shaft. Let's say there any macam company you want buy the shaft, manufacturing company lah, you want to design a machine, you need the shaft, so you will lathe the shaft. Then you cannot take the raw material, that one is hot roll. You will take the then you will lathe it. You lathe into certain, the shaft to become smoother lah, smoother and into certain diameters that based on your design. That is machine, that you lathe a machine. Okay, the shaft ni rarely we will find, unless there is a time there is a shaft, you need to be smooth surface. That is the case, but you be careful. In your exam question, they will mention in the question, they cakap the shaft is grounded, smooth ground. Kalau ground tu, you use this one, the upper line. Sometimes mirror polish ni to make it, that one is totally super smooth lah. That is rarely happen lah. Maybe there is certain case, they want it to be like that, super smooth. Okay, tapi normally, most of the case machine, so you bring your 0.87 to this one, and bring it, make sure you use your ruler, and bring it, my hand, they are using hand, crooked lah. That is your 0. For example, you get 0.7, you have to be accurate, guys. So ni you can predict 0. This is your CS. Ni 0. berapa yang saya letak lebih kurang. Ini yang tengah ni 0. berapa? Between 0.7, 0.8. Ini 0.75 yang middle kan. Ni 0.73 lah. Clear tak kelas? Hello kelas? This is how you get your surface vector. CS. Kelas? Boleh? Okay, that will be your CS. Okay, that's how you do your CS. Okay, now. Alright, CS. CT is your temperature factor. Temperature factor. Okay, tadi CS 0.73 for example lah. Okay, surface vector figure 8.13. Okay, now is temperature factor, CT. Temperature factor, if it is not given in your question, and maybe in your project, so normally you don't, normally temperature ni is not given, kita assume lah, normally when temperature factor, guys, you mean your shaft during operation, your shaft, you mount your bearing, you have your gear, you have your pulley and belt, and will drive another shaft. Okay, will drive shaft B by pulley and belt or by gear, and it's running by motor, everything, your system is running. So during that running, at the peak of running, what is dia punya maximum temperature? What is their temperature when it's running? Normally, kalau typical power transmission, normally temperature is less than 840 degree Fahrenheit. So you can go for one value lah, either for bending, axial, and torsion. Clear? CT is normally 1, tetapi unless, dulu there is an exam question, it said the temperature is 1900, let's say 900 Fahrenheit, be careful. That one is, during certain machine, dia power transmission during operating, memang yang heavy duty machine, for example like a crunching machine, heavy duty, they crunch this granular or this one, heavy duty machine. The shaft too, they have a cruncher. The shaft is rotating, they have a roller, they crunch it. The shaft too, when during, memang because it's heavy duty machine, maybe they want to drive a bigger machine, you punya shaft pulley itu, during operation, they are really in high temperature. Be careful. If very high temperature, okay, you got to use this equation. So your temperature in Fahrenheit, okay, this case for 840 degrees to 120 degrees Fahrenheit. Normally kita no longer yang bigger than ini. Kalau high temperature, if the temperature is given, guys, and it is greater, if less, kalau the given less than 140, of course you use 1, but it said 900 Fahrenheit. Okay, the one you have to use put into the equation. 1 minus in bracket 0.0032, your temperature in Fahrenheit minus 2.68 in bracket, and 1 minus that one, that would be your factor. Alright, okay. Boleh kelas? Right. Okay. The last one is CR. CR is the reliability factor. Reliability factor ni, kalau if it is not given in question, is 1. It's 1. It's 1. But sometimes in our case, sometimes we consider reliability in terms of quality. We base reliability mean how many percent fail, what will not fail. Say mean 90. Kalau 1% fail, we assume we want it to be high reliability, like 99%, the value is 0.814. If it's given in the question set, the reliability of your shaft ni, your punya system is 99%, so we will use 0.814. 95%, you use this one. But do not, I do not use interpolation. I think reliability, we don't go for 97, 90, always go for like this, 99%, 95 or 90. Kalau 90%, 0.897. Be careful guys, always look in the question. You guys got project, you know that kan? You have project, kalau project you design you punya tu, kalau say you want to go for 99%, you go 0.814. Why? Why the higher the reliability, the lower the value? Because we consider reliability. It means kalau katakan we don't consider, it means it's not given. We don't care about reliability. As long your machine is running, it means 50% reliability. Understand tak class? You don't care about it. You just want the machine to running, but you want to make your machine to be high quality because your machine involve precision, involve the safety is so important and you need precise machine. I mean the reliability must be 99%, something like that. So you 0.814, but it's just a typical machine. You just, as long the machine is running and you run the concrete mixer, for example, that one you don't care about high reliability. For example, like concrete mixer, as long as you can run the machine, you can run the drum to mix all the mixture of the cement and something lah. That one is we consider one. But unless it's your machine to really precise and you consider everything, okay, you design, okay, 97%, so this one 0.5. Okay, the point is why 50% is 1. It means kalau low reliability, because remember class kan, hello class, if you look your video, because the point here, we want to calculate our endurance limit, our CL, CG, CS, CT, CR, SM prime. SM prime also we know, SCL we know, CG we done, ini temperature we done, reliability. Kalau 50% is 1, so it means your SN will become bigger, betul tak guys? Kalau 50%. So because it means if this is 1, 50% 1, so your SN become bigger. If your I bigger, remember your basic actually SN over your SE lah. Tetapi kalau you thinking about precise, you thinking about ni, your CR ni become lower. 97% is 0.04. It means you reduce the strength. You reduce the strength of your endurance limit. So it means you really consider in terms of focus on reliability. It means of quality. So we want to make sure this one must be accurate. So it means your strength and your limit a little bit lower. Because you consider focus on safety. Be careful, like safety yang precision lah. That's why your reliability become lower lah. So ini they will reduce. Okay, clear Then you calculate so CR you based on that lah. Kalau not given 1, kalau 99% 0.4. So you just put all into this into this equation and you times by your SM prime. You know your SM prime is 0.5 SUT. Then you got your SN. Hello class. Right. So then, okay, basically nanti I will explain to you. Kita take a break sekejap, boleh Claire? Tapi the point, why do we need this calculate SN? Saya cakap SN is the strength of the specimen that you do analysis. Because we no longer use SY, kan? Because remember, basic equation certificate, your SN, endurance limit that you calculate over your sigma equivalent, your stress, kan? You punya equivalent stress. Tetapi guys, for fatigue is not like that actually, because I talking you about the rough equation. Actually, safety factor is like this, Tengok sini kelas. Your safety factor is this. More accurate is this. Safety factor, ada reason nanti I explain to you. Your safety factor is your, your sigma, like this, this your equation is your sigma, E is sigma E amplitude over your SUT. Nanti I will explain to you after the break. Your sigma E mean over ni SN. This yang SN that we calculate, where this SN is CL, CG, CS, CT, CR, SM. Ini you straight away. In fact, ini one you do first, calculate first. Okay, you know the ni SN here equal to 1 over your this is your ni safety factor. Okay, right? Kita break dulu. After the break, I explain to you what is sigma E amplitude, what is sigma equivalent mean. Okay, then SUT you know lah. SUT is your tensile strength. What is sigma EA? This is your exact equation. This one is we call, this is based on Goodman theory. Goodman punya safety factor. Based on Goodman. Okay, kita break sekejap. Kelas boleh kita break sekejap dan kita sambung balik. Okay. Hello class. For 15 minit boleh? Alright. Okay, Assalamualaikum. Minimum value, the most maximum plus minimum divide by 2. That is your sigma min. Faham guys? Class, are you hearing me? Class, can you hear me or not? Alright. Okay, another thing that we must calculate, this mean. M stand for mean, the average, sigma max plus sigma min over 2. And satu lagi, the amplitude. This one. Okay, this your mean value. The peak value to your mean is what? Sigma alternate or sigma amplitude for alternate. We call it sigma alternate. Sigma alternate is the amplitude. What is an amplitude? Amplitude is, okay, I put it in bracket because amplitude is always positive. Sigma max minus your sigma minimum, because we need the amplitude, because this is a sine wave, right? Max and min. Amplitude, sigma maximum minus sigma minimum, divide by 2. Kan? Divide by 2. Average is sigma max, because average, sigma max plus sigma min over 2. But the amplitude is the difference of this, divide by 2, that's your amplitude between your mean and at the peak. That is what you call sigma amplitude or alternate. Sigma max minus sigma min over 2. Over 2. Why I put the bracket? This one always value is always positive lah. Because sometimes your punya case, you punya graph of your plot of sigma over time, it can go for compression side. It can go for negative side instead of positive. Just not positive through time. Your sigma bending, for example, in this case, sigma bending, it could go for negative side. So in this case, in this case, kita punya sigma max is here, guys. Sigma max is sigma max apa? Bawah ke atas kalau compression. Katakan we go for compression. Hello class. Oh, yeah. Class, are you with me? Let me share you again the notes. Saya dah terkeluar tadi. Can you see my notes, class? Class? Okay, about the fluctuating stress lah. Kita kena consider lah. Kita can go, okay, if you look, the stress can go for, ni yang completely reverse, this one yang dia punya mean is 0, this one is maximum. We can go for positive side, sometimes we can go for negative side. So sometimes you can go for negative side, negative side, where your sigma mean is sigma max plus sigma minimum. Kalau negative, you have to put value negative, value negative. So it depends. And but if you look on my live video, your sigma amplitude is always positive lah. Always positive. It's not negative value. So I put it in bracket like this. Understand, class? Clear or not? Okay. You punya stress ni when plotting through time, dia fluctuate. This is the case. One example I show you, like a pogo stick, the footstep punya, what we call it, the shaft that supporting that mount, that welded here, that welded here, the shaft is critical. Based on our logic decision. Yeah, of course, as here is because we welded, then we have to study the shaft size too. Is it safe or not? It is fatigue loading because we step it at the maximum point in time. The loading is no longer static. That is fatigue, so it will weaken. The shaft too, the strength is SN. So, okay, beside that, remember that I mentioned to you about the safety factor. We have sigma E equivalent. This is based on DET, sigma equivalent amplitude, sigma equivalent mean. Sigma equivalent, because we are DET, right? We calculate all sigma equivalent, sigma equivalent, because we use DET. So we must know the sigma equivalent amplitude and sigma equivalent mean. So we put it here over our tensile strength, sigma equivalent mean. How much is it? What over our endurance limit that we calculated just now? That is equal 1 over our safety factor. Okay, that's what I cakap, macam pogo stick tu, this kind of loading lah, dia fluctuating through fluctuating. That's what we call, we always kena calculate sigma amplitude and sigma mean. That's a pogo stick lot. Okay, sometimes you have a component like, you know, a sprocket and chain. Sprocket and chain. Are you listening or not? Class, fatigue loading. Not just shaft, guys. Not just shaft. Class, are you with me? You know sprocket and chain? Bicycle. Hello, class. Bicycle, sprocket. Ya, boleh nampak videos ya? Line okay? Hello, class. Sprocket and chain. Sprocket and chain dia this is a chain. Bicycle, right? Okay, this is your sprocket lah. Sprocket have this lah. Okay. Sprocket and chain, when the cycling mounted on the bicycle, so the chain is wrapped around the sprocket like the pulley lah. When the pedaling is the full pedal, it will create tension. Because let's say you are supplier, your company manufacturer chain for mountain bike, for example. Mountain bike like Shimano, for example, like Shimano bicycle. But Shimano, they don't produce the chain. They only design the bicycle, they fabricate the bicycle or the frame, the handle. But the chain is supplied by your company. You are the vendors. So you are the engineer of that company. You as an engineer, you can calculate your chain, is it strong? Is your chain too is it because when they mount on the bicycle, when the cyclist, when the full pedal, okay, this all chain is all the same. The chain too, if we take one component of the chain, it is like this. Okay, this is a pin there. This is the chain, the mean and the plate, the metal plate is like this. So this metal plate, when it is full cycle, it have a tension. It create tension between chain and chain. So they have F maximum, and when it's not full cycle, they have F minimum. This is what we call fatigue loading. Fatigue loading. This is another case. Okay, so you have to identify. Okay, for example, you can take here, but as told you, normal case, the worst case is because we have hole here where we mount the pin. We mount the pin. We have hole here. So we at the cross section we have like this. We have a hole. We have a cross section like this. But if you consider of this fatigue analysis at this point, this is just a solid, no hole. It's like that. Okay, for example, you just focus at this point, you want to do fatigue analysis. Actually, the weakest point at this hole. Okay, what is the area? Okay, F maximum, you got sigma. You know what is your sigma axial, right? Sigma axial is because this is all axial stress. Okay, when it's full pedal, the tension, the chain, we have X maximum 10 kilonewton. For example, when it's not full pedal, the minimum force that is pulling the chain is 5 kilonewton. This is an example. So sigma axial is force time over area, right? Over area. So this is your BH. So you can use area yang deduct lah. If your focus at the center, not at the holes here, This is your BH, you know, area is BHQ. Katakan you focus, even this is not the weakest, weakest. Let's say that you focus at the center, fatigue analysis at the center, this one, at A section. Okay. Tapi actually is here, in engineer you focus ini weakest. So, okay, my point is, sigma axial F over area. Area kalau kat no holes, BH cube lah. Sorry, BH, that is stress. Axial ni we have, since we have F maximum, we have M maximum. Okay, we have sigma max, axial max is F maximum over your cross-section area. And your minimum 520, we have sigma min is your F minimum over your cross-section area. Point your interval, accession or nil, okay? Tapi in the real case, accession B lah, tapi I just want to explain to you. So this is kind of like fatigue loading also. When you plot your sigma axial stress through time, okay, this is your sigma axial over time. So it plot a sine wave, sine wave. So it go for positive, all positive. So we have sigma maximum, we have sigma maximum, we have sigma minimum. Okay, you have to sigma maximum, you calculate lah. What's your maximum force? Tadi just now I explained to you, pogo stick is bending stress. This one is axial stress. Okay, you calculate what is your sigma axial maximum, because based on F maximum, what is your sigma axial minimum, based on your minimum loading. So you calculate here, then you can know lah. Actually, you don't have to make this sine wave. So you know lah what is the value of your sigma. Class, are you with me? What is your sigma mean? Class, sigma mean. Sigma M, M is mean. Where is sigma mean is your sigma max plus sigma minimum. Plus, are you with me? Over 2. Mean is average. The middle. This is sigma mean. Class, clear or not? Hello, class. All right. So then you also have to calculate sigma amplitude, alternate. One, you can call it amplitude alternate. Sigma alternate. Sigma alternate is the amplitude. Amplitude is your sigma max minus your sigma mean over 2. This one always value the positive, pasal the value of the amplitude. Okay. Remember, yang mean ni sometimes ada value. When we go for compression tension is positive. When we go for compression, the value is negative. Be careful about that. Sometimes you have the punya maximum level dia in positive side. Dia punya minimum level in negative, but you have to use negative. So you get the average is somewhere at the middle. But the amplitude is always positive, because sigma max minus sigma min over 2. Always take the positive value. Clear tak, class? Amplitude always positive. Even you go for negative, okay, so you must calculate your sigma mean and sigma alternate, sigma alternate or amplitude. Faham? Hello, class. Class. Right. Okay, then that's why. Okay, I belum semuanya nanti last kali tentang fatigue stress concentration factor, because concentration ni when you have hole ni dia ada concentration. Tapi before that, before we go, we actually our stress must multiply. Our stress that equivalent stress must multiply. Stress that we calculate must multiply the KF. Nanti I explain to you last kali about KF lah. Tapi my point is about the, remember that I cakap you tadi about the equation or the safety factor. What is it? The main equation. Sigma equivalent amplitude, sigma equivalent mean over your SUT, sigma equivalent mean over SN equal to SL. Okay, this is why we plot. Why is it like that? When you plot, remember, when you plot a sigma amplitude versus sigma mean of your case, your analysis. So this one, the x-axis is your sigma mean. You know what is mean? Mean yang tengah-tengah. Mean, the mean, purata, average, mean. Your x is your sigma mean. Your y is sigma amplitude. Remember, our case, we are not sigma, guys. Kita sebenarnya, kita sigma E, tapi this is a plot. Why I mean sigma ni, kita equivalent. Remember, when you have biaxial tau sigma x square plus tau xy square, square root dari sigma equivalent. So we got to find sigma equivalent amplitude, sigma equivalent mean. Okay? Because our force have range. Normally in question, they will give you the force have range, maximum value and minimum value. So it means your stress have range, maximum and minimum. Then you got to calculate what is your sigma mean and your sigma amplitude based on this equation. Okay. Okay, then you plot your graph, you punya point, your sigma equivalent. Why I'm talking sigma equivalent mean, sigma equivalent amplitude that you plot into graph like this. Okay, okay. This point amplitude, this is y-axis is about sigma amplitude. The x-axis about your mean. This is positive side, this is mean for negative side. Mean negative side mean, you punya, sometimes you punya graph can go, mean can go to negative. Mean negative means that, mean negative mean, kalau your mean, if your mean go to negative because this is positive, this is negative. Kalau your mean in negative, it means you punya case, you punya all in compression mode lah. Macam ni, in case yang dalam not intention, it mean your case is all is in negative side. Ini is your sigma either bending through times, it go for negative. It mean your punya case, your loading always apply in compression, negative stress. So your mean, this is your sigma mean. This case, your sigma mean go for negative. But your sigma amplitude is always positive. Pasal sigma amplitude is max minus mean divided by 2. Sigma mean, this one sigma mean. Okay, my point is when this sigma mean over sigma amplitude plot, it go for negative. That one go for negative lah. Tapi most of the case kita go for positive lah. For example, like shaft analysis go positive. Like macam the one pogo stick, the one the step tu itu always go. Pasal dia bending tu kita go for tension side right. Tension side it goes for positive lah. Okay, for example, sigma amplitude ni, there is a limit. Sigma, this is, if you look, this is a line where your sigma mean is 0. All this line, all you point here, katakan my limit here is SUT because the most ultimate SUT tensile strength. At this point, kalau your amplitude where your sigma mean is 0, sigma mean is 0. All this line is completely reverse punya case. Nampak tak? All this line because your sigma mean is 0. Okay, you know what? Kalau you punya plot of your stress over time, kalau it mean is 0, I draw it, make sure you understand. All you punya point at long y-axis is where you punya stress punya case is like this. Your stress punya case over time, your stress that you calculate over time is like this. Completely reverse. This is another fluctuating stress, but we have max, we have mean, completely reverse like shaft. Most of the shaft completely reverse through time. Because remember, remember when shaft, this is your shaft. Okay, your shaft, you have bearing support here, and this is your pulley. You have bending and you have force here. Then you have force of bearing, and the shaft is rotating. The shaft is rotating. You can hear still hear me. So element you at the top here at this moment they're in compression, right? Pasal the shaft try to bend like this. Okay, at the top element. When it goes to the bottom, it go for tension. It goes to the top, compression, bottom, tension, compression, tension, compression, tension. It means if it is pure bending, this is what I call complete reverse. So your sigma bending here, this is your sigma bending. It goes for tension and negative value. Compression is the same value as tension, but it go for negative side. So this is tension, right? Tension, and this one is go for compression punya stress. The same value, but it go for negative side. Negative is compression, then it go for tension, compression, tension through time. So this is what we cakap completely reverse. This is completely reverse. This also fluctuating side is completely reverse. For completely reverse, it means you have sigma max. Okay, that is sigma max. Okay, this is your sigma mean. Sigma mean is equal to sigma max, but sigma mean is negative value. So this one, your sigma mean. What is that? Sigma mean is equal to what? Class? Are you with me? Class, are you with me? Kau ni tidur ke apa? Yang lain tu senyap je. Ijian aja bersuara. Lain tu saya tak tahu. Kan nanti kan. Yang lain apa? Faham tak? The rest of you, are you listening or not? Okay. What is the mean of this case? Complete reverse mean tu apa? Value mean or what? Sigma mean. Sigma mean, what value of your sigma mean here? Class? I'm asking question. I want to tengok you participate or not. What is sigma mean? Complete reverse. Maximum, minimum, same value. So, you punya purata apa? Become apa? Zero kan? Kelas. Sigma mean is zero. Betul tak kelas? Hello kelas. Kelas, are you listening or not? Yeah, sigma mean zero. Pasal logically lah, you punya maximum is tension same. Like pure bending. Element you go for tension compression. Compression bending same value as tension bending stress, right? Same value, but compression go for negative value. Tension go for positive value, negative value. Your purata, your mean is zero because we know sigma mean is sigma max minus sigma minimum. Minimum is negative side, minimum over 2. And since your sigma max equal minus sigma mean, plus, maafkan saya. Itu amplitude. Sigma max plus sigma min over 2 kan guys. Okay. So since your sigma max ni equal sigma min equal value to sigma max and it is negative value. So this one you have negative value. So it deduct, so it becomes zero lah. Class. Okay. Hello class. That is sigma min. Okay. What is sigma amplitude? Sigma amplitude is distance from here to here lah. This is sigma amplitude. You know, sigma amplitude of course you know is the magnitude in positive sigma max minus sigma min, okay, divide by 2. Okay, sigma max is the same. Sigma min is negatively the same. So 2 times of the sigma max over 2, so equal the sigma in this case complete reverse. Sigma max equal sigma amplitude, is equal to sigma max. Clear? Clear class? Alright? Completely reverse. Macam pure bending, the shaft is rotating, is completely reverse. That is not just shaft rotating. Maybe let's say you have you punya component, you have tension force, you punya tension at the time. Other case macam it goes for tension dan kemudian the next one it go for compression. It go for compression. So dia punya F tension and it goes for compression. Ada yang macam linkage then they go for tension side. Then kemudian it go for compression. It mean the tension and compression, if let's say if the force is equal, so your axial stress has compression axial stress equal value than your tension axial stress. Ada macam tu dia punya force tu equal value. Equal value. You have F maximum, you have F, kita tak cakap F minimum, so the same value. So you punya plot time is completely reverse. MF minimum. So M minimum tu negative side, but the value is the same. Value is the same. Macam there's one I explained to you before, we have range, right? 10 kilonewton, minimum is 5 kilonewton. So you go for positive. You punya ni sigma go for positive. But we have yang completely reverse punya case. Okay, this is complete reverse. Okay guys, ini all the sign macam pure bending, the shaft is rotated, is completely reverse. Okay, I just want to explain. When you plot sigma mean over sigma amplitude, all this line, ni is sigma amplitude, sigma amplitude, sigma alternate punya graph. All this line, sigma mean is zero, betul tak kelas? Kelas. Kalau all you punya stress that you calculate, ini semua case yang all this point yang you punya stress over time is completely reverse. Betul tak kelas? Kelas. Sigma lawan time. All your point along this line, along this line, where your mean is zero. Nampak tak? You punya mean, you punya positive, maximum and minimum the same value but is negative. Your mean is zero. This all mean is zero. This is graph. All you punya point along this one. Okay, yang ini SUT, limit the SUT. Pasal remember, it says that you punya amplitude, yang ini the worst, yang ini, the SUT where your mean is zero. This is a case where you punya plot of your stress, sigma stress over time, okay, this is a case where your mean is zero. It means that, okay, you punya sine wave macam ni, your mean is zero. Remember, today is complete reverse, but your amplitude, the amplitude, the alternate or amplitude we call it, this amplitude or alternate here, the value of this amplitude reach the SUT. Belajar tak? Pasal you punya complete reverse. In this case, all the point here along the y-axis, the limit SUT. If your sigma amplitude here reach, because the worst case, remember in our material kalau ductile actually is yielding kan, actually is yielding. Tapi because since the Arnold test points of breaking kan, dia punya maximum limit dia SUT lah. Kalau your sigma A is amplitude to reach the value, so this is a case SUT is the border limit. Ini yang case where you punya amplitude of your stress, kalau you punya do your analysis, the load, the stress is so high, it reach sampai so big the amplitude, complete reverse, all this point is complete reverse, SUT lah. So the SUT dia punya limit. Okay, this point here, all the point, okay, that is what y-axis. All this point here along the x-axis, this case apa? Where your punya amplitude is 0. This is case where amplitude is 0. You don't have any amplitude. This is the case. All the point along this line is the case where you only have mean saja. Okay, when is the case like we have mean? I give you one another example. Macam other case macam ni. You mean your stress plot through times, your stress plot through times, dia like this. Ini masuk apa? Stress. Ini masuk apa? We have sigma mean. Do we have sigma amplitude tak? In this case. It's like constant loading kan? It's like constant loading. Class? Are you with me, class? Yeah, I just want to tell you that this sigma m plot, all the plot yang along the initial well is your, you don't have any amplitude. You don't have any amplitude. It means your, you punya ni, you don't have any amplitude. You punya sigma mean macam tu sigma mean ada through times. Macam like constant loading lah. Static loading. You punya mean is the same. So you mean kalau you punya through time, your stress through time, dia tak ada sign waves like this is case. Ini yang cakap just about this point lah. All along this line. Where because all along the axis, all along where your sigma amplitude is 0, so we have mean. So it means that the stress is like this. Kalau sigma mean ni, kalau dia punya maksimum dia, you punya sigma mean ni, dia punya limit dia is your endurance limit. Nah, yang tadi itu, this one is about your punya amplitude. Amplitude kerana the amplitude cannot border the as ultimate tensile. And this one is about your mean. All the point here is your mean cannot go beyond you punya endurance limit. And you remember endurance limit, your CL, CG, CS, CT, CR times SN prime. Your mean. It mean your mean tu cannot go beyond endurance limit. So dia ada border. That's why you plot dia ni. This is SUT and here is your, sorry guys, aduh saya guys, Ijan, sorry, my mistake. Nanti you delete balik, boleh tak you edit the way from the point I explain to you yang ni. Just balik certain portion Sorry, saya twisted. My mistake guys. Tak, saya pening kepala dan saya dah tua. Wrong information. Kelas sekali lagi. Kelas, repeat. Remind boleh Kelas. Your sigma mean, sorry. Your sigma mean, this is your sigma mean, this is your sigma amplitude. Sorry guys. Salah, my mistake. You nanti you bagi saya atau you boleh tak you potong yang until yang the one I explain to you just now? Boleh? Can you edit it, Ijan? Can you share the view? Can you edit it? Yang the one. Oh. Boleh kan boleh klik, boleh video editing kan, you can edit it. Yeah. Tapi kalau possible lah, if you can edit yang the one tu you potong balik nanti make shorter. Saya cakap, my explain tadi terbalik guys, sorry, bahaya tu. Twisted I explain terbalik. No. This is SN. Sorry guys, tadi repeat balik. My mistake guys tadi. This is SN, the limit of this is SN, sorry. SN, my mistake. SN, it means you punya, you punya all these points, you punya, this is point where you punya mean is 0, this is mean 0. Sorry, my mistake. Be careful about it. It means along this point where your mean is 0. Your mean is 0, this is a case of completely reverse, complete reverse. Your sigma through time completely reverse. So this is your mean. Completely reverse, macam pure bending just now, is complete reverse. Your mean is 0, where your sigma max and your sigma minimum is the same value. Sigma minimum value is negative, but the magnitude is the same. So your mean is 0. Okay, sometimes in worst case, it means your but here you got your sigma alternate, right? Your sigma amplitude mean is 0. This one mean is 0, but you have your like completely, but you have value of your sigma alternate. In this case, kalau you punya sigma alternate, your amplitude ni reach. Sorry guys, pasal this what we call, this is fluctuating. This is fluctuating kan. This is fluctuating. This is fatigue. Along this one is yang complete reverse. All the point here is complete reverse. Nampak? This fluctuating punya stress. So your sigma amplitude here reach. Remember, kalau fluctuating stress, dia punya our strength is reduced. No, SUT. Sorry guys, ada twisted. SUT sepatutnya go on your axis. Our limit is SN. Remember, SN is fatigue loading because you punya stress, you punya amplitude. Amplitude mean you have maximum and minimum, but we go for complete reverse. All this yang point here is where mean is zero. Mean is zero, you punya SN, you punya limit, because it is fluctuating, is endurance limit is our strength. Endurance limit. Tadi remember, twisted tadi cakap ni SUT, pasal saya dah pening kepala dah. Okay, SN, limit is SN. So it means here, you punya, yang you punya case of you punya amplitude complete reverse. Your mean is zero, your amplitude, you punya strength, sigma A, this is strength lah, sigma is strength lah. Reach, maximum limit is SN. Where SN is just now we know kan, SN is CL, CG, CS, CT, CR, SN prime. We can calculate straightforward SN. So we plot graph. Okay, this is okay guys, this is not log 10 punya graph. Ini bukan SN curve. SN curve just now is log 10 punya graph. Okay. Tetapi yang ini you can do graph. Yang ini you can plot. Either you can plot during your exam, you can use equation or you can plot. Actually plot is better because you can see you punya location of your point, either safe or not. Amplitude, kalau complete reverse, in case where your mean is zero, complete reverse, it cannot reach, cannot go beyond SN. Over SN, the border is SN. Okay, this line, the X line here, this is where your amplitude is zero. This is a case, static loading. Okay, we have this is static loading. All this point along X axis where you punya amplitude, you punya graph, you punya stress, lawan times, dia remain straight. Static loading. Static loading kan, static loading. Remember, kalau static loading, it mean this is a case static loading. If static loading, it mean your stress tu, you have mean macam tu You punya stress over time, dia remain constant. It mean the stress is not fluctuating. They remain constant through time. So this is a case where you punya you don't have, because kalau static loading, you punya stress lawan time, you only have mean saja. You don't have no amplitude. Understand tak what I mean guys? Macam ni, you punya stress, you just have mean saja, no amplitude. Nampak tak amplitude? Amplitude is zero. You only have mean saja. Clear tak kelas? This static loading. Class, are you listening or not? Yes, yeah. Torsional strength, yeah. Sigma mean aja. Pasal sigma mean is sigma max plus sigma minimum. Okay. Over 2, right? Okay. Your sigma max same value. Right. Plus sigma mean is sigma max plus sigma minimum over 2. Kalau static loading, you have sigma mean saja. You only have sigma mean. Mean, average. That's your sigma. Because sigma mean is apa? Sigma max plus sigma minimum over 2. It's the same value of your sigma lah. Betul tak kan? Over 2. Divide by 2. Clear? Yeah, static loading means you have sigma. Yeah, biar nanti I show you. Because other case macam ni, torsional stress tu dia static. Nanti I explain to you about shaft. So, okay, dia ada combination. Ada stress, remember you punya shaft tu. Okay. Nanti I explain to you. Macam torsional stress tu they have ni. Kalau static loading, static loading, you use sigma. Kalau okay, katakan static loading, I know, I understand. What if we put into the equation, we have sigma mean, kan, right? Kan, class? Okay, but this one we using SN. Can you hear me? Hello? Boleh dengar saya? Tapi this equation meant for fatigue loading. Kalau katakan you don't have amplitude, this one is zero. Tetapi this one over SN, this one over N. Remember you SN over here, and you punya sigma equivalent over there. That is a basic static factor for static loading, right? Kan? N is here, and this one SN over. Tapi this one SN because we are now on fatigue loading. In your case, SY lah. SY. That's why. Kalau tak, my point is your question. Kalau static loading, we have mean saja. We have mean saja. Mean saja. This kind static loading lah. Through times, your maximum and minimum the same value. it means you don't have amplitude. This is considered like static loading. Remember, kalau static loading, kalau you plot static loading, okay, this all where your punya amplitude is zero, you punya limit dia, kalau static loading sebenarnya yielding kan, tetapi kita go for SUT. Tadi, sorry guys, tadi twisted cakap SUT, no, wrong, totally wrong. Correction, SUT is here. Ini go faster because all this point along the y-axis, you only have amplitude. Your mean is zero. It means it's complete reverse. This is a case is complete reverse. Macam shaft is rotated, pure bending. It means the tension and compression is remain the same, but compression value is the same as tension, but compression go for negative side. Therefore, you punya plot sine wave is your mean. Where this is your mean is zero. That is what along this y-axis, your mean is zero. This is your mean zero. This is negative mean. This is your mean zero. This is sigma mean is zero. Kan? This is your sigma mean is zero. That's why dia punya border of your amplitude cannot reach your endurance limit. Because remember, endurance limit is you punya strength that you reduce even lower than your SY because of the fluctuating. This is a case where you have fluctuating amplitude. But your case in the middle, you have combination of sigma EA and sigma M. That I show you later. So your border of Goodman line is here, guys. When you plot, this is not log 10. This is typical graph. So you make a straight line. You make a straight line, you join. So this is your punya Goodman line. Class Goodman line. Ini based on Goodman line. You with me? Hold on, Class. Clear or not? Saya dipatah dulu ya, dipatah juga. Ya, mulai. Okay, kelas. Clear or not? Ini what called Goodman line. Class, are you with me, class? Alright. So nanti when you do your analysis, you will calculate nanti your sigma equivalent amplitude. You will calculate your sigma equivalent mean because we are DET, right? We are DET. So you plot because this is your mean. So you plot where is your sigma, your equivalent, what is the value in megapascal? This one, what is the value in megapascal? Because your y is your amplitude. So you punya point sini. Okay, you punya sigma equivalent mean is here. Okay, remember I cakap tadi you calculate kan because you force you have maximum value and minimum. So you can find your stress maximum value and minimum. But our case is sigma equivalent. Remember our distortion energy theory, right? Okay, like this, what I mean is that your distortion energy, when you calculate nanti guys, you punya analysis, remember distortion energy based on DET. Remember DET, katakan you punya, for example, your shaft punya case, you add element point B. At point B punya element, you have bending of sigma X, you have bending of sigma X, and you have tau xy. You tau xy like this because of torsion, or torsion, tau xy. So you calculate. So you don't have to make more circle actually. Kalau you have bi-axial stress, okay, you know your stress value. Tetapi remember, your stress value, remember tak? Your force tahu ada max, ada min. Are you with me guys? Kan? You punya force ni ada pasal nanti in question nanti you punya force ni ada maximum and minimum value. Macam tu lah contohnya. Ataupun kalau you complete reverse macam ni. Kalau sebenarnya kalau shaft normally sometimes equation for shaft dia tak bagi force pasal shaft is rotating. Your shaft is rotating. Katakan you have support at here and you have a point where you mount your pulley and this one is gear, so you already calculate your shear diagram, something on SY even I just make it rough lah. You punya XY plane, Z plane kan, remember you buat your shear diagram like this, then you punya moment at B, let's say moment at B and both plane is at this is is critical. For shaft analysis, they don't have force maximum, force minimum. Your force is just one value, then you calculate your moment. But remember, the shaft is rotated. Okay, the shaft is rotated. You look side view, the shaft is rotating. It means your element ni, you punya plot of you punya bending stress, okay, remember, okay, let's say at point B ni, you combine both XY plane and XZ plane, which one yang ni, remember you do analysis guy, previously you do analysis on shaft kan, combine on both plane XY and Z, the total moment at B, where moment at B, you have total moment at B, square at, XY plane, and total B at XZ plane square. Because B is total latest moment. So you know your bending stress. Bending stress at B ni, bending stress at B, okay, at B, you punya bending stress is 32 moment, total moment here at B over your pi d cube, diameter of your that section B. What's the diameter of the shaft? So you punya moment ni, sir, my moment ni is just what is the maximum minimum value. Okay, in this case, you punya case yang ni, your bending ni, you punya plot, you punya bending through, you punya sigma bending through time, dia like this. Your sigma bending through time, dia sine wave. Pasal dia completely reverse. Because you punya element, at point dia reach tension side, it go for positive, it go for negative side, it go for negative. And value is the same. Go for negative compression side, sigma, same magnitude, but negative value. Nah, are you feel me or not? Boleh nampak saya punya kan? Right. And tension, it go for positive value, but the magnitude is the same. So it means for bending, it is completely reverse. You only have sigma bending have only amplitude. You have only alternate only, but the sigma mean, your sigma mean is zero. Is zero. For bending is zero. But your tau xy for your shaft, your tau xy torsional stress, torsional stress. For torsional stress, for shaft, the torsional stress. Okay, dia tau torsional stress over time, but torsional stress the straight line. Clear tak kelas? Because at element B ni, kan, at element on your shaft tu, the torsional stress, the shaft is rotating. But the torsional stress, because like this, you punya shaft, okay, this is your shaft, your shaft. This at element B punya circumference. Remember, if your element at the top, it become tension. It goes to the bottom, it become compression. And this is bending because of your sigma x. Sigma x. So it means your bending stress to it go for completely reverse. You only have sigma bending amplitude, but your sigma mean is zero. I'm talking about sigma bending over time. But if this is your shaft, okay, this is circumference of your element, your torsional stress like this, betul tak kelas? Torsional stress going this direction. Class, it keep rotating along the circumference. Torsional stress. Class, are you with me? Faham tak pasal kan? Yeah, tak apa. Okay, torsional stress along the circumference, it remains the same. It means your torsional stress, tau xy tu kan, torsional stress, along ni, the shaft, because the shaft is rotating, RPM, betul tak? Is rotating. Your torsional stress along the circumference, does it change? Is it the same? Macam bending, at the top it go for tension, at the bottom it go compression, it change. But the magnitude is the same, but it change. So we have sine wave, right? Sine wave, our mean is zero. Clear? Clear or not about bending? Alright, okay. Also at element B, we have torsional stress, right? Always we have torsional because of the pulley and gear. Between the B and C, we have torsion, right? We have torsion. At torsion tu, the shaft, okay, this is your section B punya circumference. This is your shaft, I buat isometric mode. The torsional stress along the scope, the shaft already. It means torsional stress tu, you punya element tu akan go like this. And we have always torsional stress along the circumference. And the shaft is rotating. Through times, the shaft rotating. Through time, the torsional stress, does it change magnitude or remain the same? Remain the same, right? Class. Understand? It's constant, remain the same. I mean, torsional stress through time, straight line. Clear? But bending completely reverse. But we have sigma amplitude. Ini normally case for the shaft. For bending, okay, shaft, we have normally shaft, we have combined that, we have torsional stress and plus your bending stress, like this. Okay, for bending, always is a sine wave and it completely reverse. It means sigma mean is zero, but we have amplitude. But torsional stress, it remain constant value a long time. So I draw it again, make sure to understand. So for shaft, okay, normal case of shaft, normal case of your shaft, the bending always completely reverse through times. Okay, this is your through times. This through times. So your sigma mean is always this will called completely reverse because the element at A, your point at section B, your element at the top go for tension, then rotate because the shaft rotates. So element go to down. Bottom is compression, up is tension, bottom is compression, tension, compression, tension, compression. I'm talking about your bending stress. Bending stress. Bending stress direction in terms like X lah because they're bending kan. Bending stress. It go for bottom, it go for compression. Up, it go for tension because the shaft is rotating. You mean your element too is rotate up and down. Yeah? They circulate. They circulate. Because your bending will facing positive and negative. Tension and compression. That's why they have sine wave. So the mean is 0, but you have sigma amplitude. You can calculate sigma amplitude. What is sigma amplitude, sir? Sigma max minus sigma min. Sigma amplitude, sigma max minus sigma min divided by 2 is a positive value. Sigma min y0, of course lah, sigma max and sigma min the same value because sigma min is sigma max plus sigma minimum over 2. Since your sigma minimum is negative, can. So it means 0, can. Complete reverse, it means your minimum is 0. Okay, kalau you complete reverse, your bending is because maximum is this go for tension, this is for compression, and your mean, and since the same value, compression tension same value as compression negative value, the magnitude is the same. Of course, the middle is mean is 0. Clear class? Clear tak? Complete reverse for bending. Normally shaft ni case Clear or not? Guys, boleh dengar saya ke ni? Alright, apa? Okay. Tetapi saya cakap, kalau you punya tu, yang tu saya cakap torsional stress kan? Torsional stress, macam you buat specimen, torsional stress this direction kan, this direction. Torsional stress, kalau torsional stress is allowed, you punya circumference, okay, going downward, torsional stress. The shaft is rotating, this remain the same value. Pasal torsional stress does not facing tension, they don't have positive torsional, negative torsion, pasal they remain, they is rotating. Torsional stress, your element to remain the same, it is rotating kan, element is rotating, but the torsional stress does not vary through time, remain the same value torsional stress and the same direction. It does not go, can put that at that time, go for this direction, no. It remain at that direction because the shaft is rotating lah. Clear? So that's why your torsional stress through times, torsional stress through time remain straight. What is torsional stress? 16T, 16 kalau solid shaft, 16 times torsion over pi d cube. What is bending stress? 32 moment pi d cube. Ini only untuk solid shaft, not hollow. Hollow lain. MCOY, torsional stress, TR over J. Be careful. Okay, jadi torsional stress remain the same. So it is remain the same. We only have, do we have amplitude tak? Do we have alternate? Do you have tau alternate? Torsional also stress. Do you have tau alternate? Class in this case, right? Ada alternate tak? Alternate mean, macam ni kalau you ada maximum, minimum, you ada alternate. You ada amplitude. Amplitude. That's alternate or amplitude between your mean and the peak. Ini ada mean and the peak tak? So what is tau mean? We only have what? Do you have tau alternate? Well. Mana pukul? Kita sampai pukul kelas. Ini dah pukul 11 ni, sorry dah. Okay, selepas dah kelas, dah overtime kelas. Dan kita sampai pukul 11 kan? Okay, soalan boleh saya tambah sikit boleh tak? Okay, so yang ni, you only have tau mean. You only have tau mean. You don't have tau mean. Ni tau amplitude is 0. Okay, tau amplitude is 0. Okay, class, hold on, just a little bit more. Okay, that's why. For example, like shaft ni case. Okay, I want you to look. Okay, can you see the notes? The notes. And also I share you the textbook. Okay, you look, highlight, you bookmark on this on your textbook. Hold on, I share the textbook. Mana textbook? Okay, can you see the textbook? Nampak ke lah? Can you see my textbook? Class? Okay, the textbook. Okay, take note on this page. Look at this page. Page ni. Ini yang combine yang sigma A kan. Okay, tengok kelas you punya ni textbook ni page 301 ni. Okay, you highlight, make sure you bookmark this one. Okay, this equation, these two equation, sigma EA ni and sigma pasal kita dissociate. So we have to calculate because kita DET with sigma equivalent stress sigma equivalent amplitude alternate or amplitude call sigma alternate is amplitude sigma E alternate equal to sigma A square. Terus ini kita take note. Sigma E mean, lepas you kena calculate this two. You kena calculate tu. Okay, you look on my my ni. Okay, the equation is, okay, when you calculate, you punya sigma E amplitude, pasal kita sigma equivalent nak, equal to, okay, equal to, remember tak you punya, kalau you have biaxial stress kan, sigma equivalent equal to sigma x square plus 3 tau xy square, that is sigma equivalent. Tapi kita ada both, kita kena calculate you have to find sigma equivalent stress alternate amplitude and you have to find also sigma equivalent mean. You have to find, okay, sigma equivalent amplitude, our alternate is square root your sigma alternate square plus your 3 tau alternate square. Okay, and okay, sigma alternate square. Okay, untuk case shaft, hello guys, kita nak calculate sigma A untuk shaft. Do we have alternate shaft pure bending? Ada tak? Shaft, kata kita ada tadi sigma and tau torsional stress, right? Do we have sigma alternate tak kelas? Shaft untuk case. Pasal kita nak find equivalent. Do we have sigma amplitude tak? Do we have amplitude for shaft? Ada tak? Ada kan? Bending. Pasal bending ada sigma. Sigma is bending. Tau tu torsional. Okay, torsional. Ada kan? Amplitude. Yes, we have value this one. Okay, 3 tau amplitude untuk case shaft. Ke shaft. Do we have amplitude untuk tau? No, zero. So this one become zero. Tapi you use the equation, this one become zero. So you punya sigma EA equal to sigma amplitude. Betul tak? Your sigma lah. Your sigma 32 moment pi d cube lah. Okay, sigma amplitude. Because sigma amplitude for complete reverse is the value of your sigma max. Kan? Okay, is sigma amplitude. So, this one is straightforward. You punya yang bending 32 moment pi untuk this one untuk case shaft lah. Bending stress, okay. Or your sigma x. Okay, now the second equation, if you look on your textbook, okay, now kita want to find sigma E mean. Okay, the equation that given the text on your ni, on page ni, on your page 301 ni, okay, sigma E mean. So sigma E mean is sigma mean over 2. This equation you must know. I can take note about the equation. Sigma mean over 2 and tau mean square plus sigma mean over 2 square. This is a basic question. I'm talking yang my sample case is shaft new case. Okay, you punya shaft new case. Do you have sigma mean on shaft? Shaft biasa bending is mean is 0. So sigma mean in sigma ni stand for bending. Kalau shaft sigma normally for bending lah. Tapi be careful kadang-kadang you combine dengan axial stress because for that also sigma. Okay, for shaft kata bending and torsional stress Normal case lah macam you did your assignment. Okay, this is the question. Do you have sigma mean? Bending ada mean tak? Ada mean tak? What's the value of sigma mean here? Plus. Yeah, 0. This one 0. This one because sigma mean is 0. Okay, tau mean ada tak? Do you have tau mean? Torsional stress tak sikit. Torsional is constant kan? They have mean. Kan? Tau mean ni is your 16T over pi d cube lah. Your solid shaft, right? Tau mean, class. Ada kan? Yellow class? Yes, we have tau mean. Yes, we have tau mean. Sigma mean ada? Sigma mean ada apa?
Tak ada.
0. Ini bukan untuk all case kan, ini yang case like shaft ni 0. So you punya sigma EM equal your tau mean. Pasal ni square root equal your tau mean. So this yang value kita cakap. Okay, this is our sigma EA is sigma amplitude, sigma EM is tau mean. Okay, then yang saya cakap you plot into this graph kan. Then saya cakap you plot into this graph. Sorry, saya dah over. Itu yang tadi. So, you calculate your sigma EA value. Okay, this is your punya plot of your graph. Okay, yang tadi cakap sigma mean versus sigma A. Sigma is your y-axis. So, this one your border is your SN. This one, the border is your SUT. So when you make a straight line, it's like that. Okay, straight line like this. Okay, then you plot, you punya, okay, you calculate. Sigma EA, what's the value? Okay, this is amplitude, right? Okay, amplitude is your sigma A. You plot sini. Okay, this is your sigma A punya value. You get in megapascal to Ising, and you calculate your sigma EM. Your sigma EM equal to M. To M is 16 T over pi d cube. So you put your sigma, this, since this one actually is your sigma EM. Okay, this is your point, loading point. This is your, okay, make it here, for example here. You get your sigma EA is there, sigma EM is there. So this is your point. This is your punya point. Memang safe lah, pasal you below the line. After the line is not safe. After the line not safe, below line safe. Below the line. Pasal ni you punya limit. Ni good man line. Good man line. Good man line. Okay. Good man line. So you punya point ni, okay, you can get your safety factor by make like this. That's why kalau you have normally kan you punya graph, kalau mathematical equation, kalau you punya graph like this is your origin, you punya mark your y-axis is Sn, your mark as x-axis is SUT, macam itulah, and this is your point. That's why safety factor sigma EA that you calculate this one over your Sn plus, okay, sigma EA over your Sn plus your sigma EM, your mean, you calculate over your SUT equal 1 over n. Selalu macam tu Kalau you punya line is like this, okay, you punya equation to get safety factor is like, the equation macam ni, 1 ni over 2, ni over ni equal to 1 over n. Understand class? This is a Goodman punya equation, Goodman line punya equation to find the safety factor. Understand class? You find your certificate CMEA, you get it. Sn, you remember you calculate CL, CG, CS, CT, CR, Sn prime. That one straightforward. SUT get from table property tensor strength. That is sigma A, sigma N. That's your safety factor. That will be your safety factor. Okay. Or you can use graph. Here sigma EM, you go for this. So this one become SM pun boleh pakai if you don't want to use graph. Yang ini will be your strength amplitude. Your safety factor is, pun boleh pakai graph, is your SM over the value of your value of your sigma EM over sigma EM. Also the safety factor is your SA here, SA over your sigma EA. Pun boleh, same value as you get this one. Ini kalau you tak nak use graph, use direct use equation. Tapi the disadvantage of use equation, kadang you cannot see you punya point. Where is you punya point yang ni lah. You can see. Tetapi one thing before kita quit one class, satu lagi yang kita point of consideration, kita ada satu nama yielding line. Kita kena tengok sini. Even katakan we plot, ini our sigma amplitude and this is our sigma mean. This is our Sn, this is our SUT. This is our SUT. Okay, this is our Goodman line. Okay, remember, kita ada, okay, atas sikit Sn, kita ada yielding. Yielding, ini also yielding. Remember, SUT is ultimate tensile strength, yielding is a little bit lower. Remember, ductile material, yielding tu dia dah berlaku failure. Dia dah start behave, when it reach the border of yielding, they already behave like elastic. Only dah consider fail. We got to consider. This is yielding line, either amplitude or mean. When we join SY, we kena buat line ni juga. Yielding line. Okay, this one point of consideration. You kena consider ini nama dia Langer line. Langer line is the SY. Because sometimes when you plot, kadang-kadang, okay, kalau you tak buat equation, you tak buat pakai graph, you don't use graph, you just use equation, you get, okay, you punya sigma your Sn tadi untuk Goodman, your Sn over sigma EA plus your SUT over sigma E mean equal to 1 over you punya safety factor, right? You punya safety factor. Tetapi you just calculate your safety factor, you get 1.2 safe. But you punya point ni kadang-kadang memang ada safe because this is your Goodman line yang ni. You punya point is here. It's safe memang pasal this is Goodman line. It looks safe on Goodman. But you punya point ni yang point of consideration. Ini yang kita kena consider. Sometimes your point is here. But when you calculate Langer line punya equation, Langer line is this guy. Langer line is your punya SY. So because ini adalah sigma amplitude, your SY over your sigma E amplitude plus SY over sigma EM equal to 1 over N. Let me check. You punya equation of your from your notes. Equation on ledger line. This equation, if you look on the notes, you can see my note. Ledger line ni, oh sorry guys, saya ni dah, guys, sorry. Equation for terbalik guys, saya, yang ni betul. Simak ni, Goodman ni betul. Simak ye Goodman betul. Ni, sorry guys, repeat. Saya, pasal kita 1 over N. Kalau Goodman is apa? Sigma EA, you calculate over your SN. Plus that, sigma E mean that you calculate over your SUT. Bukan tadi, saya terbalik tadi yang tu, this one denominator. Equal to 1 over N, because this 1 over N, okay? This Goodman. Sometimes when you calculate your Goodman, you get it 1.2, it could look like the same, but when you calculate the Langer punya equation, you dah reach, actually you dah over the border of yielding. You dah over the border. Your point is here. It looks like on Goodman it's safe, just beyond the, just before your Goodman line, but it's over the yielding line. SY. You mean your point tu, itu dangerous tu. You mean you have got to change your size lah to make you totally safe dalam ni you punya safety factor. Because when you calculate you punya Langer because this is SY, it means that your sigma E amplitude that you calculate over your SY plus your sigma E mean over your SY juga equal to 1 per N. But kalau you tak pakai graph, kalau you calculate you punya ni is 1.2 something, 1.27. Safe lah. But you calculate, you put the SY value, your sigma, you got ni 0.9 something. Fail. Why? Sebab apa dia kat sini? Dia dah over the yielding line. That's what we call the yielding line. Dia dah over. So be careful. Ini mean you have to adjust lah. You got to adjust, change you. Kalau you punya project lah. Sometimes in test, they ask you question, you don't have to adjust. You just they ask you to find both. Just calculate. So you make your judgment from there. But on Goodman, it's safe. But on Langer line, it's over already. You get less than 1. Be careful. It means kalau in your project you design, it means you have to increase the size, diameter of the shaft, increase the size of the, atau you change the material yang stronger. That's how you do it lah. So you redesign balik the shaft to make sure that you totally fall into this. Kalau you fall into, you punya safety factor 4, 6 something like that lah. Depend on you punya value lah. Okay, class, sorry thank you. I hope you understand. Yijian ada record Yijian. Sorry lah, it's solid 3 hours because ini fatigue memang dia condemn. Fatigue is quite difficult lah compared dengan lain. I hope you understand. Siapa yang tak faham, for you not understand, you try to look at the video, try to understand what I'm talking about lah. And you can look the note that I share to you, and also you can read the chapter textbook on chapter 8. Impossible lah you want to change because component design ni you don't read the whole chapter kan. Take the most important part, the one that I mentioned in this video, also in the notes. Take note, make sure you see my video and tengok, repeat balik. If you hard to understand, you repeat balik. Apa yang what I try to ni lah, explain to you. I hope you understand. I stop it here because kita ada another part yang I tak fokus lagi. Nanti on the second lecture, nanti kita go, that's another one more topic about stress concentration factor. Because shaft ni, dia not plain, dia ada stress concentration. Stress concentration, it means the shaft tu, pasal I cakap, the shaft ada shoulder. They have shoulder, they have ni, the stress concentration. We have KF value. KF ni have to multiply with all your sigma amplitude. KF ni have to multiply with your sigma EM. Kena multiply. Ni is fatigue stress concentration factor. Because shaft ni, even point B ni ketika, tapi shoulder is the worst. Pasal dia ada fillet. Okay, certain shaft we have a groove also. A groove. This point of consideration, not just at point B. B is the most moment at SY plane. No. Sometimes you have to look on the groove because they are the groove. Some shaft they are the groove where we mount you punya washer kat sini to lock you mount your washer at the groove to lock your pulley. Pulley will not get misalignment. Stay at the position. They can ada snap fit ring put here. So you have, on the shaft have curve, have this groove. Groove ni will raise you punya stress concentration better. So it will raise your stress here is much higher compared with just plain no groove. So that's why we have to multiply by fatigue stress concentration better. This one I will explain in the next topic. Okay, sorry for taking your time. Nanti I also in next topic we go for sample problem. Alright, okay. Okay, thank you very much guys. Kita go for attendance. Faham kau ni? Aku cakap ni boleh Yelah, betul tak kalau tengok? Yelah, I think, yelah if I'm not mistaken, yeah. Cuba check, double check. Kita test drive cover static, fatigue, and satu lagi gear forces. Itu je. Gear forces bukan gear strength. Just a simple one. Gear forces, calculate forces of gear. 3 question. Apa tu? Yalah. Apa? Tengok balik course online tu mana ni? Ni. Lecture plan. Cuba tengok. Your lecture plan. Boleh nampak? Boleh nampak tak? Dia tak sebut. Can you see the lecture plan? Can you see the lecture plan? Week 8 Ni after raya kan? 8.5. Yeah. Kita still on, kita week 4 right? Kita on track lah. I'm starting fatigue. Fatigue ni actually 2 topik guys. Kita sampai next week je. Tapi next meeting ni, kita ada next meeting on Wednesday punya kelas ni. Kita kena buat sample problem. I got to explain to you about the sample problem. You can see lah, you do sample problem. Ada one topik tadi yang fatigue stress constipation, I haven't mentioned yet. Itu on the next ni. Okay, kelas? Okay, kita go for it. Hold on. Ini section 8 kan? Section 8 kan? Okay. Sorry for taking your time. Okay. Thank you very much. Assalamualaikum warahmatullahi. Scan your attendance. Oh, tak nampak. Okay. Hold on. Okay. Scan your attendance. Assalamualaikum warahmatullahi.
Thank you, Doctor.
Thank you, Doctor.
Welcome.